What would it be like to live on a planet traveling around a star so huge that, in comparison to it, our sun looks like a tiny speck of dust? Well, you could find it out if you manage to visit a planet orbiting WOH G64. It's a red supergiant, an enormous star dwelling in the Large Magellanic Cloud, which is a satellite galaxy located not too far away from our home Milky Way galaxy. Red supergiants in the Large and Small Magellanic Clouds provide an excellent opportunity to observationally test the current stellar evolution theory for massive stars. WOH G64 is likely the largest star we have found so far. It's a real heavyweight emitting an incredibly bright light. To understand the sheer size of this megastar better, let's put it into perspective. Compared to our star, the radius of WOH G64 is around 1,540 times bigger. In other words, it's like comparing a tiny grain of sand to a basketball. If we placed WOH G64 at the center of the solar system, the surface of this star would extend past the orbit of Jupiter, swallowing up Mercury, Venus, Earth, Mars, and Jupiter itself. You see, the average radius of Jupiter's orbit is around 1,000 times the radius of the Sun. As for Saturn, the radius of its orbit is around 2,000 times the radius of the Sun. That's why WOH G64, with its average radius being 1,500 times the radius of the Sun, fits right in between. Oh, and if you spread out the star's dust envelope, it would cover a distance of about 1 light year, or 5.88 trillion miles. The star is not only ginormous, but also immensely bright. In fact, it's one of the most luminous stars we know of. Luminosity is the total amount of energy a star emits per unit of time. And the light coming from WOH G64 is around 282,000 times brighter than the light from our sun. But perhaps one of the most amazing features of WOH G64 is the dust envelope surrounding it. In 2007, astronomers, with the help of the Very Large Telescope, discovered that WOH G64 was surrounded by a torus-shaped cloud. It's so thick that to some extent it obscures the star. The dust envelope is made up of the material the star has expelled, and it contains between 3 to 9 times the mass of the Sun. The star we're talking about was discovered in the 1970s by Bengt Westerlund, Olander, and Hayden. That's where the WOH in the name of the star comes from. It's an abbreviation made up of the first letters of the discoverers' names. By the way, Westerlund also discovered another remarkable red supergiant, Westerlund 126. It was spotted in a massive star cluster called Westerlund 1 in the constellation of Ara. But back to WOH G64. Scientists have noted that this star lies very close to or even beyond the Hayashi limit. It is a theoretical constraint upon the maximum radius of a star for a given mass, a condition where the inward force of gravity is matched by the outward pressure of the gas. By now, the star WOH G64 has reached such an evolved state that it can no longer hold onto its atmosphere because of super low density, high radiation pressure, and relatively opaque products of thermonuclear fusion. That's why its average mass loss is among the highest known to us so far. It's unusually high even for a red supergiant. WOH G64 also shows an unexpected spectrum of nebular emissions. The hot gas is rich in nitrogen and has a radial velocity more positive than that of the star, which is quite an unusual phenomenon. The star might have a potential companion, an O-type main sequence star. If it turns out to be true, then WOH G64 will be classified as a binary star. At the same time, so far, there have been no confirmations of this theory, partly because the intervening dust clouds make the examination of the star very difficult. In any case, WOH G64 is absolutely fascinating, not only because of its huge size, but also because of its unbelievable luminosity and mysterious dust envelope. It's a great example of how unexpected and amazing our universe can get. Besides, such outstanding large stars are undoubtedly an important astronomical observation. The results of studies of such objects correct the restrictions on the properties of stars within the framework of modern models. For testing the applicability of models, the exceptions to the rules are most valuable.
Stargazers, come up here, because I have exciting news. Astronomers have just completed the full mapping of 2 pairs of stars outside our Milky Way galaxy that are chowing down on their stellar neighbors. Not only does it give us a better understanding of stars in general, but it can also help us measure distance in the night sky. Did you know that more than half of the stars in our Milky Way are paired? And while it's unlikely that other galaxies have a significant number of binary stars too, they're usually too faint to see. But these so-called symbiotic stars, where one star consumes the other, are extremely bright and easier to observe. And, according to scientists, measuring the orbits of these symbiotic star systems is an essential step towards learning whether other galaxies create binary stars like those in our Milky Way. Now, let's get down to the nitty-gritty. A pair of stars may be born together, but due to their masses, they age differently. The more massive one burns through its material faster, reaching the end of its lifetime first, and leaves behind a compact white dwarf. White dwarfs are small and dim, but can pack the mass of the Sun into an object the size of Earth. If close enough, their gravity can pull material from their companion, creating a signal that astronomers can identify from far away. Draco C1 and Lin 358 are the symbiotic stars that have been fully mapped. The stars in Draco C1 take roughly 3 Earth years to orbit one another, while Lin 358's components take just over 2. These are the first full orbital measurements of any symbiotic star system outside the Milky Way. The new measurements will help astronomers better understand star formations in other galaxies. In some symbiotic stars, the white dwarf can slurp enough material from its companion that it explodes in a supernova. These supernovae are incredibly bright and can be seen across the universe. They all start out with the same brightness for a nearby observer, making them like a sort of standard candle for measuring the universe. While Draco C1 and Lin 358 are unlikely to explode as supernovae anytime soon, understanding how they work can provide us with a better understanding of how these standard candles evolve. If you're here to complete your knowledge of weird stars in the universe, don't be disappointed. We're not finished just yet. Have you ever wondered about the biggest stars in the universe? Scientists have recently discovered a gigantic star called WOH G64. This bad boy is located about 9,500 light-years away from Earth and is truly out of this world. It's about 1,700 times larger than our Sun, which means if it were in our solar system, it would reach past Jupiter's orbit. There's more. WOH G64 isn't just massive, it's also super bright. It's what scientists call a red supergiant, and it shines with a brightness of about 340,000 times that of our Sun. If you're thinking about getting a tan from this star, think again though. It's way too far away for that. How does a star like WOH G64 even form, you might wonder? Well, it starts out like any other star. A cloud of gas and dust collapses under its gravity and starts to heat up. Eventually, the temperature becomes hot enough in the core of the cloud to ignite nuclear fusion, and a star is born. But WOH G64 didn't stop there. It kept devouring more and more gas and dust, growing larger and larger. This process continued until it became the giant we know today. As fascinating as WOH G64 is, it's not the only big star out there. There are others, like VY Canis Majoris, which was once thought to be the biggest star until WOH G64 stole the show. VY Canis Majoris is still a force to be reckoned with though. It's about 1,400 times larger than our Sun, and located about 5,000 light-years away from us. But here's the kicker. Stars like UY Scuti and VY Canis Majoris aren't even the biggest things in the universe, not by a long shot. There are objects called hypergiants that make these stars look like ants in comparison. One such hypergiant is Stephenson 218, located about 20,000 light-years away. It's about 2,150 times larger than our Sun and shines with the brightness of 7 million suns. And just when you thought things couldn't get any crazier, there's a mysterious object called the Great Attractor that's pulling everything in our local group of galaxies towards it. We don't know what it is or what's causing it, but one theory is that it's a massive cluster of hypergiants. We'd be minuscule in comparison. The next star is so metal, it's practically headbanging all the time. Jokes aside, scientists have discovered a star that's called a heavy metal subdwarf. Now that's a band name. It's a type of star that's seriously heavy metal. This star has more metal in its composition than any other star we've seen before. Such stars are said to contain metal elements like iron, nickel, and chromium. This heavy metal subdwarf has about 10,000 times more iron than our Sun. In their discovery, astronomers used a technique called spectroscopy, which involves analyzing the light that comes from the star to determine what elements it's made of. By looking at the spectrum of light, scientists were able to see that this star had an unusual amount of metal in its composition. There's more. This heavy metal subdwarf isn't just a regular star with a lot of metal. It's also really weird in other ways. For one thing, it's smaller and cooler than our Sun. And for another, it's really old. We're talking about a star that's been around for almost as long as the universe itself. What does this all mean? Well, scientists are hoping that by studying this heavy metal subdwarf, they can learn more about the early universe. Since this star is so old that it was around when the universe was just beginning to form, it's seen a lot of stuff. By studying its composition and characteristics, scientists can get a better understanding of what the universe was like in its early days. This next star is one of the coolest things in outer space. Her name is Vega, and it's one of the brightest stars in the night sky. Some recognize it as the shiny point of light in the constellation Lyra. And get this, it's only about 25 light-years away from us, which in astronomical terms is practically next door. Scientists have been studying Vega for a long time, and they've learned some pretty interesting things. For starters, Vega is a young star, only a few 100 million years old. That might sound like a long time, but compared to our Sun, which is around 4.6 billion years old, Vega is practically a newborn. Vega is also a very hot star, with a surface temperature of around 17,000 degrees Fahrenheit. To put that into perspective, the surface of our Sun is only about 10,000 degrees Fahrenheit. So if you think it's hot outside today, just be glad you're not hanging out on Vega. Another interesting thing about this star is that it's surrounded by a disk of dust and gas. This disk is called a debris disk because it's made up of leftover material from when the star formed. Scientists think that this debris disk is similar to the one that surrounded our solar system when it was young. Vega is also a source of cosmic rays. These rays are high-energy particles that zip around space at incredible speeds. They're made up of protons, electrons, and other particles, and scientists aren't exactly sure where they come from. But they do know that Vega is one of the places where cosmic rays originate. But wait, there's more! Vega is also a famous star in pop culture. It's been used in a lot of movies and books as a source of inspiration, mostly because of its brightness and cool features.
Check out this interstellar showstopper. Shadows doing a little dance in space have spilled the beans on a mind-boggling secret about our solar system's origins. There's a star called TW Hydrae that's playing host to some mischievous disks that are out of sync, spinning at slightly wonky angles. But what's causing this celestial chaos? Well, it seems like a bunch of baby planets are misbehaving, tugging at the disks with their gravity and throwing everything off balance. Hold on tight, because things are about to get even more interesting. This star is a real newbie in the cosmic neighborhood at just 8 million years old. Yep, that's practically a cosmic toddler compared to the ancient Sun, which has been around for a whopping 4.6 billion years. This new start hasn't even started its hydrogen-burning season yet. It's still in the process of growing and compacting under its own gravitational pull. Think of it as the Sun's younger doppelganger. Here's the lowdown on how stars like TW Hydrae get their groove on. They gather cosmic dust and gas from their surroundings, which forms a swirling disk around them. This disk is like a cosmic buffet for planet formation. Little specks of matter come together, forming bigger and bigger clumps that eventually collide and grow into full-fledged planets. Since they're born from a flat disk, these planets usually end up orbiting their star in a neat, flat plane. Now, our new star has struck gold with its unique orientation. We're lucky enough to have a front-row seat to this cosmic construction site because we can see the disk face on. And guess what? It looks a lot like our solar system. This gives us a chance to uncover some juicy secrets about our own planetary origins. Back in 2017, eagle-eyed astronomers noticed a shadow making its way around this new star's disk. It completed a full rotation every 16 years. Initially, they thought this shadow might be evidence of a sneaky young planet forming within the disk, causing parts of it to wobble in different directions. Fast forward to 2021, and things took an unexpected twist. The shadow did something totally unexpected, leaving everyone scratching their heads. Hold your horses, though. The savvy team of astronomers didn't give up easily. They put their thinking caps on and came up with a few possible explanations. After extensive modeling, they hit the jackpot. It turns out not just one, but 2 wobbly disks were at play, casting shadows on a third outer disk. This suggests the existence of a second young planet, making it a cosmic double feature. Imagine these 2 planets zooming around, one trying to outpace the other, like a pair of racing cars. The data suggests that the first disk is about 5 to 6 astronomical units from the star, while the second disk is around 6 to 7 astronomical units away. For reference, our mighty Jupiter orbits the Sun at a distance of 5.2 astronomical units. So, it's like a cosmic game of tag with the planets influencing each other's orbits. As these planetary misfits go about their orbits, their gravitational interplay causes the disks to tilt slightly with respect to one another. This creates shadows that dim the outer regions of the disk. Oh, and by the way, this totally matches our own solar system vibe. Why? Because some of the planets in our own solar system are rebels too, and have orbital inclinations that vary by up to 7 degrees. I'm looking at you, Mercury. Or a whopping 17 degrees if you count our dear friend Pluto. Who knows? If we continue researching this new star, it might just spill the beans on how our own solar system's got its funky orbital inclinations. How exactly do we define our solar system, though? It's like a celestial neighborhood with 8 funky planets happily orbiting our sun. In order of proximity to the Sun, we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Oh, and we can't forget Pluto, our little dwarf planet friend who used to be part of the Planet Club. Our solar system is way more than just the sum of its planets. It's like a fantastical mashup of asteroids, comets, stars, moons, and a whole bunch of other spacey stuff that makes our cosmic home truly enchanting. Contrary to popular belief, the hottest planet isn't the one getting all cozy next to the Sun. Nope. It's Venus, the second closest planet. How come, you might ask? Well, Venus is scorching because it has an ultra-thick atmosphere. It's basically like it's wearing 100 layers of sweaters. When sunlight pierces through this super dense atmosphere, it turns Venus into a fiery furnace. We've also got some rocks on Earth that are like interplanetary tourists from Mars. Can you believe it? Scientists have found these rocks here, and they're chock full of the same gassy goodness found on the red planet. How did they get here? The most plausible scenario is that Mars sent a souvenir package through an asteroid crash or volcanic fireworks show. Our planet is also the ultimate chemistry whiz. Sure, other planets have bits and pieces of the elements we have, but we've got the whole shebang. Iron, oxygen, silicon, sulfur, magnesium, sodium, nickel, calcium, aluminum, if you can name it, we most likely have it here somewhere. Other planets are like, hey, we're mostly rock with helium and hydrogen, but we're here with our unique blend of interstellar awesomeness. Jupiter, however, the heavyweight champ of our solar system, has a never-ending party happening in its atmosphere. It's called the Great Red Spot, and it's been swirling with hurricane-like intensity for more than 300 years. This stormy event boasts extremely powerful winds, reaching a blazing 270 miles per hour. Oh, and by the way, this colossal storm is more than twice the size of our entire Earth. Neptune, on the other hand, knows how to make an entrance. It's got the fastest wind speeds in the solar system, zipping around at more than 1,200 miles per hour. Just like Jupiter and Saturn, Neptune actually produces more energy than it gets from the sun. As it turns out, Neptune's energy comes from its core, and that's what powers its super-duper strong winds on the surface. Now you might be wondering, how does Neptune manage to keep all that energy to itself? Well, it's all thanks to a special blanket of methane gas, which acts like a cosmic snuggie. This snuggie, or rather greenhouse gas, traps the heat and keeps it cozy on the planet. If Neptune were a bit more like Uranus, which is a bit of a slacker in the energy department, all that heat would have gone on a space vacation ages ago. Despite the chilly temperatures, Neptune doesn't let it bring down its funky style. It radiates a whopping 2.7 times more heat than it receives from the sun. It's like Neptune saying, "Hey sun, you're cool, but I've got enough heat to make my winds wild and crazy." Space isn't as far away as you might imagine. The Kármán line, which is approximately 62 miles above Earth, is like the official starting point of space. If you could drive your car straight up into the sky, you'd actually reach that mark in less than an hour. That's even quicker than some people's daily commute. As it turns out, our solar system is actually already halfway through its estimated life cycle. Scientists estimate that our solar system is around 4.6 billion years old, and it's expected to keep going strong for another 5 billion years. We've still got a lot of time left in this celestial ride. In the meantime, the Sun, our fiery superstar, will keep trying to pull the planets towards it. Talk about being clingy. Gravity on the Sun is so powerful that it's constantly exerting its pull. But don't worry, the planets are not just passive participants. They're like determined tug-of-war players, pulling in the opposite direction and keeping a fine balance. As a result, the planets end up kind of floating in the middle. It's no wonder the Sun has so much power around here. The mass of the Sun is mind-blowingly huge. In fact, the Sun's mass is around 330,000 times that of our beloved Earth, and get this, it accounts for over 99% of the total mass in our solar system.
Most of those twinkling dots scattered across the night sky seem unreachable. But one of them is Beetlejuice, a star so enormous and nearby that you can see it with the naked eye. To find it, locate the first 3 big dots in the Orion's belt. A reddish star to the left is Beetlejuice. It's one of the brightest stars we can see from Earth, and it's just 640 light-years away. No big deal. Beetlejuice has a blue-white O-type star, which is one of the hottest types to exist. Beetlejuice was scorching hot, reaching temperatures of about 90,000 degrees Fahrenheit. Although that was back in the day, now it's an elderly star, and it cooled down to just 5,800 degrees. You know, vacation weather. Blue-white stars are absolutely massive and burn incredibly bright, because they have loads of hydrogen fuel. But they have a price to pay for this glory. They burn through their fuel super quickly. As they age, they transform into red giants. This is exactly what happened to Beetlejuice. It burned through its hydrogen and started burning helium instead. This caused its outer layers to puff up like a balloon, turning it into a red supergiant and making it one of the largest stars out there. Now it's stretching over 700 million miles in diameter. Now it's about 1,000 times bigger than our Sun. If Beetlejuice replaced it, it would swallow up Mercury, Venus, Earth, Mars, even Jupiter. And its atmosphere would almost reach Saturn. But something strange has been going on. Beetlejuice spinning way faster than it should for a star of its size. Huge stars like Beetlejuice are expected to rotate slowly, but it suddenly started spinning at a rate of about 3 miles per second. Thanks to powerful radio telescopes, Beetlejuice's orange-red surface can be seen in detail. That's how we learned that it often changes its brightness. Sometimes Betelgeuse shines super brightly and then gets very dim. This happens about every 400 days. And recently, a telescope called ALMA, which is made up of many antennas working together as one, showed that Betelgeuse's surface seems to be moving unevenly. It's like one side is coming towards us while the other is moving away. But all of it might be a trick of light. Betelgeuse isn't as smooth as our sun. Instead, it's super chunky. Its surface is like a boiling cauldron. It's bubbling and churning incredibly fiercely. Imagine giant plumes of hot gas erupting from its core, reaching the surface and then vanishing back inside. And these bubbles are bigger not only than the sun, but Earth's entire orbit around the sun. These bubbles also rise and fall super quickly, even faster than a spacecraft. And maybe this tricks our telescopes into seeing it spin faster than it really does. Some astronomers also think that Betelgeuse could have swallowed up another star, and this gave it a spin boost. But these are all just theories. Things got even more complicated when Betelgeuse dimmed once again, this time in a pretty unexpected way. What's interesting, it was discovered using a weather satellite. A regular telescope had a hard time seeing Betelgeuse clearly because of Earth's atmosphere. So they used a satellite that normally watches Earth's weather, but can also take pictures of space. As we mentioned, it usually brightens and dims about every 400 days. But recently, it suddenly dimmed by 2.5 times more than ever before. This event got the name the Great Dimming. The first theory said that Betelgeuse cooled down and sneezed out a bunch of material, creating a massive dust cloud. This cloud blocked the view of the star, making it look much fainter than usual. They also noticed something strange happening to that dust. It started behaving differently, which might be a sign that something deep inside the star was causing trouble. Betelgeuse's brightening and dimming cycle now happens faster in just 200 days instead of 400. And to add to the mystery, in the spring of 2023, it started shining even brighter than it normally does at its peak. Why is this frightening? Because Betelgeuse might be preparing for its grand finale, and this wouldn't be very good for Earth. We might be on the verge of a supernova. When massive stars like Betelgeuse run out of fuel in their cores, they start burning different elements like carbon, oxygen, and silicon. Eventually, they end up with iron in their cores. At that moment, everything changes. Adding helium to iron doesn't produce energy like other reactions do. Instead, it sucks up energy. This causes the star's core to collapse, leading to what's called a core collapse supernova. A spectacular, breathtaking show. Supernovas are so bright that they can outshine entire galaxies. But a Betelgeuse supernova would be special. Because it's relatively close to us, it would be so bright that we could see it even during the day. When it happens, Betelgeuse will shine as brightly as a full moon, but all that light will be concentrated in one point. For about 2 months, it will be so bright that you could read a book just from the light of the supernova, even if you turned off all the city lights and had a clear sky. The idea of witnessing Betelgeuse explode as a supernova is truly thrilling. After all, the last time a star went supernova in our galaxy was way back in the time of Johannes Kepler, more than 4 centuries ago. That event, known as the SN 1604 or Kepler supernova, dazzled the sky for weeks. But don't get too excited yet. We're not sure when exactly it'll happen. One study says that the star might be in its carbon-burning phase. If we're near the end of that stage, then Betelgeuse might blow up very soon, during the next tens of years. But it's nearly impossible to determine because during that last phase, the star barely changes at all. Even though Betelgeuse is close enough for us to study its surface, we can't peek inside its core to see what's really happening with it. We might as well be at the beginning of the carbon-burning phase, and in that case, we might have to wait 1,000 more years before that cool supernova. Another study says that Beetlejuice might have less than 300 years of fuel left in its core. They say that Beetlejuice is known to expand and contract regularly, and its pulsation pattern hints that Beetlejuice is much larger than we previously thought. This would suggest that the star is further along in its life cycle and closer to going supernova. Other guesses come from observations of similar stars. For example, a star called VYCMA in our galaxy is thought to be closer to going supernova than Beetlejuice, and it's been dimming steadily over the past century, unlike the relatively stable Beetlejuice. If Beetlejuice was about to go supernova, it would dim steadily and very quickly. Also, historical records suggest that about 2,000 years ago, people saw Beetlejuice as yellow, not red. If that's the case, then we might be in its early last days after all. In other words, we have no idea whether it will go supernova tomorrow or in 1,000 years. We just gotta wait and see. But let's say it goes supernova tomorrow. What happens to us then? The 1987 supernova in the Large Magellanic Cloud showed that the effects from the supernova might be so strong we can sense it even from very far distances. The Large Magellanic Cloud is almost 170,000 light-years away, and we still detected the radiation. It's kinda hard to say exactly what the danger zone is. A rough estimate could be around 100 light-years. Luckily, Beetlejuice won't pose any danger to humans. It's hundreds of light-years away, and its supernova won't influence us in any way. We'll be able to enjoy its supernova beauty without any harm.
A space mission like this has never been done before. Nearly 20 years in the making. It's so precise that even a millimeter of error could ruin the whole thing. 2 satellites are floating hundreds of miles above the Earth with one big goal: to create artificial solar eclipses on demand. This could change how we study the Sun forever. But pulling it off is insanely difficult. And let's just say, NASA and the ESA are holding their breath. Proba 3 has successfully launched and already shows promising results. It's made up of 2 satellites that will fly in perfect formation. Their goal is to block out the Sun in space. Well, why do we need that? Because solar eclipses are actually very useful for studying the Sun's corona, its glowing outer atmosphere. The Sun is obviously super bright, so its corona is only clearly visible during rare fleeting moments when the Moon perfectly covers the star during an eclipse. But what if we could recreate that effect anytime? That's Proba 3's main task. One satellite acts as an occulter, a giant sun-blocking disk. It also carries a wide disk about 5 feet wide, which acts like an artificial moon, blocking out the Sun's light. The other is a coronagraph. It should capture detailed images of the corona. There's also a third device that should study space weather and how solar storms affect our planet. It's insane how perfectly precise they must be for this to work. They must stay perfectly aligned with their position shifting by no more than a single millimeter, about the thickness of a fingernail, all while they're floating high away from Earth in space with no strings attached. This project was a team effort and a pretty big historical moment. This is the first time that an ESA mission is launched from India since 2001. Proba 3 was built with contributions from 13 European countries, along with Canada. There was a small hiccup before departure, though. The air freight company refused to accept the satellites because their batteries were still inside. The engineers had to remove the batteries and ship them separately. Not ideal, but a small price to pay for getting the mission to the launch pad. The idea first came to mind in 2005 to ESA scientists, and after years of planning, designing, and testing, the mission finally lifted off on December 5, 2024. For the first few weeks after launch, the 2 satellites stayed connected. Scientists run tests to ensure they were functioning properly. During this time, the coronagraph took its first ever space image. It captured a beautiful star field in the Ophiuchus constellation. Then, on January 14, 2025, the real mission began. The two spacecraft successfully separated from each other. Over the following weeks, ESA's engineers carefully brought them back together to keep controlled distance. Now that they're in orbit, Proba 3 satellites work in a highly elliptical orbit, swinging between 372 and about 37,000 miles from Earth. This should help ease the Earth's gravitation, meaning the satellites won't need to burn as much fuel to stay perfectly aligned. The spacecraft also communicate with each other using lasers, adjusting their distances in real time. This level of control has never been attempted on this scale before. But the Proba 3 mission isn't only about looking at the Sun. The second satellite, the Occulter, has its own mission. It carries DARA, an instrument that will measure the Sun's total energy output. This is incredibly important for climate studies. Scientists need to know how much solar energy reaches Earth. If Proba 3 succeeds, it'll prove that satellites can fly in space autonomously while staying super precise. This could open the door to entirely new types of space missions. For example, giant telescopes in space, where separate satellites act as one enormous lens. Or more advanced climate monitoring with precision instruments orbiting Earth together. Finally, deep space exploration. Spacecraft could team up to explore planets and moons in ways never seen before. 2025 is going to be full of insane space missions. It's packed with lunar landings, asteroid visits, and planetary flybys. But space is never easy. Missions get delayed, some never launch, and others surprise us. First, IMAP, Interstellar Mapping and Acceleration Probe. This one will launch in September, and it should help us unlock the secrets of interstellar space. It will travel super far away to study the boundary between our solar system and interstellar space. This mission will help us learn more about cosmic rays, solar winds, and what happens when the Sun's influence stops and the actual terrifying space begins. Next, PUNCH and SPHEREX. These two were already launched on March 11, 2025. PUNCH will help predict solar storms before they hit Earth. It will track solar winds from the Sun to Earth and help us understand space weather better. Space weather is important because it can damage satellites and power grids. And SPHEREX will map the entire sky in infrared light, capturing the spectra of millions of galaxies. It could reveal the secrets of how galaxies formed after the Big Bang. Next, we've got TON-2, which should launch sometime in May. It will visit the legendary asteroid Kamao'aliwa. Many years ago, this asteroid might have been a chunk of the Moon, and now it orbits the Sun. The next one is ESCAPADE. Once again, two spacecraft, one Mars mission. ESCAPADE should be launched somewhere during 2025. It will send two small spacecraft to Mars to study how the solar winds influence our red buddy. Many years ago, Mars used to be like early Earth. It had a thick atmosphere and liquid water, but it's now a dry, cold desert. ESCAPADE will help us understand what exactly happened. How and why did Mars lose its atmosphere? 2025 will also be packed with lunar missions. Unfortunately, not all missions are going to be successful. For example, the IM-2 lunar lander reached the Moon's surface on March 6th. It was supposed to land near the Moon's south pole to search for water ice. Finding water on the Moon would be incredibly important for our future human missions. If we find a method to turn this water ice into normal water, we'll be able to build entire settlements there. Well, IM-2 was marched on February 27th. It traveled to the Moon successfully and prepared for landing. It made it to the surface, but something went wrong. Communication was lost temporarily, and no one really knew why. When NASA re-established contact, they saw that the lander wasn't in the correct position. One of its two radio antennas wasn't working. Turns out it landed sideways, and now solar panels can't generate enough power. And without power, the lander couldn't keep working. By March 7th, the battery was completely drained and the mission was over. But there are more plans. In late 2025, they should launch the Griffin lunar lander. The rover it will bring should explore the Nobile crater, a key target for future moon bases. In somewhere between 2025 and 2026, they want to try the IM-3 lunar mission. It's going to be a third lander with multiple science experiments. Now, what about the planets? NASA's Europa Clipper is currently headed to Jupiter's icy moon Europa. Scientists have suspicions that this place could have water. It might even become a place for future human missions. On March 1st, Europa Clipper flew by Mars and used its gravity to speed up. On August 31st, ESA's JUICE spacecraft, another one that aims at Jupiter's icy moons, will fly by Venus. They might even snap some pretty pictures along the way. Finally, Juno's mission nears its end. Since 2016, NASA's Juno spacecraft has been orbiting Jupiter. It gave us breathtaking images and crucial data. Now, it's running out of time. If all goes as planned, Juno will continue until September before being deliberately crashed into Jupiter to avoid contaminating its moons. All these missions are pushing the boundaries of human knowledge, and we're just getting started. Imagine if somewhere, trillions of light years away from our world, there's another version of you watching this very video right now. Not as crazy as it might sound. The multiverse theory is having its time of the day, from Marvel's movies to Spider-Verses to the recent famous hit Everything Everywhere All at Once. But it's not just some wild sci-fi concept. Physicists have been talking about this theory for decades. Let's see what they say. Do parallel worlds exist? If they do, let's hope that this is the reality where you click that subscribe button before diving into the video. Now, everything starts with the Big Bang. Before the Big Bang, the universe, with everything we know, was crammed into an unbelievably tiny, super hot, and mega-dense point. Our universe is about to burst into existence. And then, boom! The most colossal event you can imagine happens. In an instant, this tiny point expands with indescribable speed. It's the beginning of everything – time, space, and all the galaxies that surround us. Then, like an extremely hot balloon, the universe started stretching out in all directions, which sounds logical, but what's curious is that this inflationary epoch lasted for an incredibly brief time, in less than a blink of an eye. It's like the universe hit the fast-forward button, and then everything eventually slowing down over time. After this speedy phase, the universe kept growing, but at a more normal pace. This rapid expansion is called inflationary cosmology. It explains some big mysteries about our world. It tells us why it looks the same in all directions, why the background radiation is evenly spread, why galaxies are where they are, and so on. The details of how this cosmic inflation works are still a bit mysterious, but scientists are on it, and the theory itself is universally accepted. But it wasn't always this way. To scientists, this idea sounded like insane sci-fi at first. However, it explains so many things that the scientists just had no choice but pay attention to it. However, its initial weirdness was just the beginning. Now, according to this theory, inflation might not be a one-time thing. It could be happening repeatedly, maybe even endlessly. Picture the universe as a never-ending cycle, with each burst of inflation creating its own bubble universe. And the most important thing is that these bubble universes might not play by the same rules. Some could be totally weird, where the laws of physics are going crazy in ways we can't even fathom. Which means there might be a whole constellation of bubble universes out there. However, we can't directly see these other bubbles. They exist beyond the edge of our spotlight. That's where the multiverse theory comes into play. People have been chatting about the idea of multiple universes for a long time, like way back in ancient Greece. Now, back in the 1990s, people got really interested in this idea, and this concept started popping up in books and movies. As a result, scientists began talking about it increasingly in scientific discussions and journal articles. And nowadays, many scientists and philosophers are into it. Now, the problem is, there's no solid proof or evidence that these other universes really exist. It's not a proved or confirmed theory. It's not even a theory at all, just a hypothesis, a bunch of interesting thoughts put together. Before we draw any conclusions, we need much more in the way of clues and evidence, and unfortunately, it's hard to find the evidence of parallel worlds when we can't live or look past our own. which is why many scientists believe that it might not be real. But not everybody agrees with that. While critics say that we can't observe the multiverse and therefore can't test it, some physicists suggest a different approach. Instead of trying to find these parallel worlds, we could try to look at ours and its history. Around the 2010s, researchers took a closer look at data from a space gadget called the Wilkinson Microwave Anisotropy Probe. Yes, that's a mouthful. They thought they found signs suggesting that our universe might have bumped into other universes in the past, like sort of a collision. But then scientists used an even fancier satellite, which had 3 times better resolution, looked at the data more thoroughly, and didn't find any strong proof of these universe collisions. Plus, there was no evidence that other universes were tugging on ours with their gravity. However, an interesting discovery happened in 2015. One scientist checked out radiation left over from the Big Bang. He claimed to see something super bright, 4,500 times brighter than expected. Well, at least based on the stuff, like protons and electrons, scientists think existed in the early universe. So he and some others assumed that this might be our first evidence of our universe crashing into others. But let's assume that it does exist. The multiverse wouldn't be about human decisions creating alternate timelines. In quantum mechanics, it's not human decisions that split everything into parallel worlds, but the measurement of subatomic particles. So if we look at this theory scientifically, other worlds would be billions of light years away, and what's happening to them wouldn't have anything to do with our daily choices. So what would it look like? Well, Max Tegmark, for example, talks about 4 levels of universes and multiverses. Level 1 is the extension of our world. Our universe is a big place, and in an infinite universe, there would be infinite chunks like ours, each with its own story. Most of these chunks might look different from ours, but because there are so many, some might look just like ours, but they'd be really, really far away. Level 2 is a universe with different physical constants. This idea says that our universe is part of a much bigger space where bubbles form. Each bubble might have its own set of rules, like different laws of physics. Level 3 is the many worlds interpretation of quantum mechanics. This one's a bit tricky. In the quantum world, things can be weird. Imagine rolling a dice. Each number that comes up might create a separate universe. So if you rolled a dice and got a 3, in another universe, it would be a 6, and so on. Yeah, my head's spinning. This idea suggests that every possible outcome in quantum events creates a whole new universe. And level 4 is the ultimate ensemble. This level gets super abstract. It says that everything, every possible universe or reality, can be described using math. I wish now I hadn't fallen asleep in algebra. Imagine all the different math equations describing every conceivable way the universe could be. This level says that every math equation that can describe a universe actually exists, and they're all real in their own way. Stephen Hawking was a proponent of the Level 3 many worlds interpretation. It was one of his last theories before he passed away. He predicted that the universe is finite and far simpler than many current theories about the Big Bang say. According to Hawking, the universe is like a giant quantum system, a sea of possibilities and probabilities. In this view, every outcome of the universe's history plays out in parallel existences, and we, as observers, play a crucial role. Our existence and what we observe, according to Hawking, actively shapes the universe we see. In simple words, the universe is a canvas and we're all painters. Sounds very cool and insane, but hey, many things in science were considered crazy before they turned out to be true. So, is there another copy of you somewhere watching this video and who just pressed the like button? Who knows? If there are infinite copies of us, scientists assume that we might be like identical twins, sharing the same origins and starting from one thing, but then developing into separate different people. And if these worlds exist, perhaps we can even visit them one day. There could be some connections between us, something that could allow for interdimensional travel, for example, wormholes. Well, whatever the truth may be, let's hope that one day we'll discover it. Until then, stay curious.
Hop on board. Hurry, we don't have much time. We're on a cosmic journey to find the biggest star in the universe. The first star we pass is our own sun. By far, not the biggest one out there, but it's still massive. You could fit 1 million Earths inside it. That means if you think of the sun like a basketball, Earth would be half the size of a pencil eraser. If we put all the planets on one side of a scale and the sun on the other, the planets wouldn't stand a chance. The sun makes up 99.9% of all the mass in the entire solar system. Mass is basically how much stuff or matter something is made from, and it's what you can thank for stars shining. You see, the more matter in a star, the thicker and hotter its core becomes. This starts a chain of chemical reactions. Hydrogen atoms get smashed into each other to form helium, releasing an incredible amount of energy. That's the star's light and heat. So, bigger stars also equal brighter ones. But with all those reactions going on, this shortens a star's lifespan. When it starts to run out of fuel, the star will enter the giant phase. It'll expand and turn red. Which brings us back to the task at hand. The biggest star we'll find is likely to be on the edge of its life. Switching on our hyper light engines, we soon arrive at the Lumen 16 system. Here, we'll find one of the smallest stars out there, a brown dwarf. Small here means about the size of Jupiter, but they're small for stars. Brown dwarfs are also called failed stars because they don't have enough mass for those chemical reactions. That means they're not as bright, but they're super dense. All the matter in them is packed together so tightly, they weigh 80 times more than Jupiter, even being the same size. And if you think that's something, just look at a white dwarf, even more tightly packed. This one here is Sirius B. It's also about the size of Jupiter, but it'd weigh as much as the sun. It emits a dim white light. Once it runs out of gas, it'll turn red and cool down. Now let's fly closer to its giant neighbor, Sirius A. You easily see this star from Earth, no telescope needed. Twice heavier and more than 1.5 times wider than our sun, it's the brightest star in our night sky. Now we fly 550 light-years away from Earth to the constellation Cassiopeia. Almost 100 years ago, a cosmic explosion happened here. It expanded the atmosphere of the star Gamma Cassiopeia, and some gases were thrown into space. After that, it became the brightest star in the constellation. It's 10 times wider than our sun. On to the famous North Star. Funny enough, different stars have had this title over the years, and more will take it in the future. That's because Earth's pole star changes every 26,000 years. Imagine our planet like a spinning top. The northern pole will shift around in a little circle, pointing at different stars to the true north. The current one is a supergiant 37 times wider and 5 times heavier than our sun. It's easy to find in the night sky. It's on the very tip of the Little Dipper's handle. Get ready now. We're setting off for the eye of the storm, the center of our Milky Way galaxy. To see the next star, we need to switch to infrared mode. This pistol star is hiding from us in space dust. In just 20 seconds, it emits as much light as our home star does in an entire year. And its size is jaw-dropping. It's 420 times wider than the sun. But it's still not the most luminous star known to humanity. That would be a blue supergiant in the constellation Triangulum. Meet B416. It's almost 10 million times brighter than the sun. But the brighter a star, the faster it burns up all its fuel, and the shorter its life. Compared with a red dwarf that barely glows and burns fuel much more slowly, its life will be hundreds of thousands of times shorter. 3,400 light-years from Earth, there's one of the rarest celestial bodies in the universe. It's a yellow hypergiant called Rho Cassiopeia. Among the countless stars in our galaxy, there are only a couple dozen of these. And even though this star is extremely far away from our planet, you can still see it in the sky without needing a telescope. That's because it's 300,000 times brighter than our Sun. It also helps that the thing is 900 times wider than our home star, too. And its color tells us that its fuel reserves will last for a long time. When Rho Cassiopeia starts to turn red and expand, it'll be one of the biggest stars in the entire universe. Now, we move to the constellation Orion. The star is in our sights. Beetlejuice, one of the largest ones visible to the unaided eye. 700 times the size of our Sun. If it took our star's place, its surface would touch the asteroid belt. That's between the orbits of Jupiter and Mars. It would engulf the 4 inner planets, Earth included. But this star has astronomers very excited. They predict Beetlejuice will explode in a fantastic celestial show in the next 10,000 years. It'll be the greatest astronomical event of all time because we'll be able to observe a supernova at a close but safe enough distance. The exploding star will shine as bright as a half moon. It'll be visible in the daytime sky for a year and at night for several more. Now we venture to stars that exceed the Sun's width 1,000 times. Mu Cephei is a hypergiant boasting the title of the reddest known star. Its color tells us that the fuel gauge is getting closer and closer to empty, but it's still so big that it could hold 1 billion suns in it. And because of its mass, this star will eventually become a supernova or even a black hole. Let's take a trip of almost 4,000 light years from home. Here it is, a red supergiant called VY Canis Majoris. It's one of the biggest and brightest stars of the Milky Way. It could fit 3 billion suns. And even though it's so huge, this thing is surprisingly light, only 17 weights of the Sun. In the context of celestial bodies, you could call this star an inflated balloon. In the next 100,000 years, VY Canis Majoris will explode in a hypernova. Gamma radiation will destroy all life in the local part of the universe. But this star is so far from our solar system that it wouldn't mean any harm to us. If we placed MY Cephei in the center of our solar system, it would bulge all the way out to Saturn's orbit. To remind you just how far away Saturn is, think of it this way. It takes the Sun's light 8 minutes to reach Earth. To get to Saturn, it takes well over an hour. Compared to this massive star, the Sun is just a grain of sand. It's one of the most luminous and reddest stars in our universe. The bigger and redder the star, the closer it is to its end. So, we're not looking at just a titan of the universe, but also one of the oldest celestial bodies out there. The second biggest star in the universe is UY Scuti. It's about 1.5 billion miles wide, 16 times the distance from the Earth to the Sun. This is a pulsating variable star. Its brightness changes about every 2 years. UY Scuti is a record breaker in fuel combustion per year. Scientists expect it to evolve back to hotter temperatures like a yellow giant. Our journey is coming to an end. Before us, we behold Stephenson 218. It takes 20,000 years for light from this star to reach Earth. It's hard not to see this red supergiant on our tiny terrestrial home. It's 2,150 times wider than our Sun. We'd need 10 billion suns to fill its volume. For comparison, the average beach contains only about 5 billion grains of sand.
Imagine a being so powerful it can suck in entire galaxies, so mysterious it's invisible to the naked eye, and so impressive it bends the very fabric of space and time to its will. Yes, meet my mother. Just kidding. Actually, meet the ultimate superhero of the universe, the black hole star. What is it and how does it work? Well, let's find out. The universe is full of marvels, and the black hole star is one of the most impressive ones. It's a supermassive force that can bend the laws of physics and a true enigma for scientists to unravel. No wonder science fiction writers find them so captivating. A black hole star, also known as a quasi-star, is a hypothetical type of extremely massive and luminous star that may have existed early in the history of the galaxy. They're predicted to be as luminous as a small galaxy. But unlike modern stars, They weren't powered by nuclear fusion in their cores. A quasi-star's energy would come from material falling into a black hole at its core. And yes, just like a normal black hole, these stars have the power to suck in anything and everything that gets too close, including stars, dust, and even entire galaxies. But how is it possible that the star is born from a black hole? And what's more, how do they continue to coexist together? Well, first let's discuss how black holes are born in general. It all starts with a supermassive star, one that is at least a few times more massive than our own Sun. This giant of a star burns bright and hot, shining with the light of 1,000,000 suns. But eventually, it runs out of fuel and its fate is sealed. As its lifespan comes to an end, it makes one final massive boom, a blast so powerful it can outshine an entire galaxy. This blast is called supernova. During this boom, the outer layers of the star fly away, while the core gets squished together by its own gravity. If the squished core is heavy enough, it can keep squishing until it becomes a black hole. And just like that, a black hole is born. Don't even try to put diapers on this thing. Now, this cosmic monster baby can continue to grow by swallowing up anything that comes too close, including stars, dust, and even entire galaxies. This is basically what's happening now in our universe with supermassive stars. But what about quasi-stars? The formation of a quasi-star could only happen early in the development of the universe, before hydrogen and helium were contaminated by heavier elements. And because of that, quasi-stars have one important feature. They are gigantic, so enormous that it's literally impossible to imagine. They may have been dwarfing even the largest known modern stars, like VY Canis Majoris and Stephenson 218. No wonder they're so scary. They were born from protostars, one of the first stars in the universe, the great-great-grandfathers of, everything. So now imagine a protostar so massive that its core collapses into a black hole, just like we described before. But the key difference is that in a regular supernova, the outer layers of the star are blown away by the energy released during the boom. Meanwhile, in a quasi-star, these outer layers are massive enough to absorb the energy without being blown away. What do we get in the end? A star with a black hole in its core that weighs from 1,000 to 10,000 solar masses. This quasi-star is about 14,000 times bigger than our Sun, which makes them bigger than any star we know today. These celestial titans have some pretty crazy properties. Once a black hole is formed at the center of a giant protostar, it starts to give off a ton of energy. This energy helps to balance out the force of gravity, making it kind of a giant fusion-based star. They would be so bright that each one would look like a small galaxy. Quasi-stars would have a pretty short lifespan, around 7 million years. Just for comparison, our Sun is about 4.5 billion years old, and it's only halfway through its lifetime. But either way, during this short period, the black hole at the center would grow to be about 1,000 to 10,000 times the size of our Sun. Quasi-stars are also thought to be super hot, with temperatures reaching over 17,500 degrees. But as a quasi-star gets older, it starts to cool down, and its outer layers become see-through. Eventually, it cools down to a temperature of 6,740 degrees, and at that point, it's curtains for the quasi-star. It can't survive at that temperature, so it just dissipates, leaving behind an intermediate mass black hole. Unfortunately, right now, there's no observational evidence for the existence of quasi-stars. This is because they're thought to have only existed a very, very long time ago. They may have been very massive population 3 stars, which are extremely rare and difficult to detect. It's also very unlikely that any of them would still exist today because of their super short lifespan, only 7 million years. So why do scientists believe that quasi-stars could have existed? Because they're looking for ways to explain how supermassive black holes formed so early in the history of the universe. They're found at the center of most galaxies. But how could these monsters have formed so quickly? After all, it takes a really long time for small black holes to grow into supermassive ones. This is where the idea of quasi-stars come in. These stars aren't just destructive forces of nature, they're like the black belts in the martial art of gravity. They can bend and twist anything to its will. That's why these stars, if they really existed, had to play a crucial role in the evolution of galaxies. They must have been instrumental in shaping the universe as we know it. So, those intermediate-sized black holes that they left behind could eventually turn into supermassive black holes in the center of galaxies. But we're still yet to solve this cosmic mystery. Detection and study of black hole stars is like trying to find a needle in a haystack. Only instead of a needle, it's an invisible and mysterious object. And instead of a haystack, it's the vast expanse of space. But with the help of some pretty cool technology and a lot of brainpower, scientists are getting closer to uncovering the secrets of these celestial giants. Here are some things that can help us in this research. First of all, gravitational waves. They're like ripples in the fabric of space-time, caused by the movement of massive objects. Albert Einstein predicted them way back in the 20th century, but they were finally detected only in 2015. We caught them by observing the collision of two black holes. This discovery confirmed that black holes can merge and that they're a powerful source of gravitational waves. Scientists think that by studying these waves, they can learn more about how black holes form and grow. We can also try to detect quasi-stars by observing the effects of their gravity on nearby objects. It's like trying to spot a criminal by their fingerprints. For example, if a black hole is located near a star, scientists can observe the star's light being distorted as it's pulled toward the black hole. And of course, we can use our technologies, such as X-ray, infrared, and radio telescopes. This allows us to study black holes in various ways and at different stages of their lives. In other words, scientists are working hard to uncover the secrets of these celestial giants. We develop new telescopes, search for primordial black holes, and try to understand the connection between black hole stars and dark matter. And we're making some pretty incredible discoveries, just like with gravitational waves. All these things will bring us closer to uncovering the secrets of quasi-stars. And when we find out the truth about them, it will become a new page in our scientific history.
Stars are beautiful, colorful things. There are red giants. Those are nearing the end of their lives and are on the verge of explosions. Blue stars shine in the belt of the constellation Orion, as well as other places. Yellow ones, like our sun, are pretty ordinary. They're usually warm and stable enough to support life. But look at the night sky attentively. Do you see any green or purple stars? Nope. They're kinda invisible because of the way we humans perceive visible light. The color of a star mostly depends on its surface temperature. The hotter it is, the shorter wavelengths the light it emits will have. The hottest stars are blue or white blue. Those are some of the shortest wavelengths of light. Cooler stars are normally red and red-brown, which are longer wavelengths. At the same time, stars never send out their light in just one wavelength. It's more of a range of light. The wavelengths of light from a star peak in just one color in a bell-shaped curve. But the star emits other colors too. Human eyes have evolved to see yellow and green radiation, probably because our sun emits it mainly in these wavelengths. But a green star emits radiation right in the center of the visible light spectrum, in all possible colors. That's why such stars appear white, which is a combination of all hues. Actually, our sun emits quite a lot of green light, but we perceive it as white. Purple stars, though, are something our eyes won't ever see because they're sensitive to blue light. And since stars emitting purple light send out a lot of blue light too, because these shades are next to each other on the visible light spectrum. The human eye picks up only the blue light. When it comes to other objects in the solar system, many planets seem to have no obvious hue. Look at Venus, Saturn, or Jupiter. They look kinda bland, probably whitish at best, but there are several planets that boast very decisive colors. For example, Mars looks orange-red, Neptune is blue, and Uranus has a beautiful blue-green hue. The planet gets it from all that methane gas in its atmosphere. Meteors sometimes display a vivid green too, and look at breathtaking bright auroras. Green is the most common color of the northern lights. But not stars, never stars. The brightest star in the sky, besides our sun of course, is Sirius. It's twice as bright as its competitor, Canopus. located in the southern constellation Carina. Being the most brilliant, Sirius is very easy to identify. Probably the coolest thing about this star is that it seems to be changing its color. But we'll get to it a bit later. This star is whiter and hotter than the Sun. Its surface temperature is 17,300 degrees F, while the Sun's surface temperature only reaches 10,000 degrees F. When you combine the immense heat Sirius emits with its girth, 1.75 times the size of the Sun, you'll understand why the star looks so bright in the night sky. Sirius has a companion star. It's called the Pup. It's a tiny but incredibly dense white dwarf with a diameter of a mere 7,000 miles. This makes it smaller than Earth. At the same time, its mass reaches 98% of that of the Sun. It means that the matter inside this tiny star is squeezed very, very tightly. That's why its gravitational pull is 350,000 times greater than Earth's. A person weighing 150 pounds would weigh 50 million pounds on this star. Now, Sirius is famous for its twinkling. And since it is also the brightest star, we can observe the ever-present turbulence in its atmosphere quite well. As for the star changing its color, it has to do with the atmosphere of our planet. Pockets of air at different temperatures focus starlight this way and that like small lenses. We see it as twinkling. But since white light is made of different colors, one pocket might send some red our way. Another will send blue or yellow in totally random order. That's why it seems that Sirius twinkles in color.
Castles were cold places in times past. The stone seemed to radiate the winter chill. This is one practical reason why tapestries were hung upon castle walls, to help keep the cold out and the warmth in. But you just can't hang any old thing on castle walls. It should be beautiful, heroic, with a heavy wow factor. The ancient Greeks hung tapestries on the walls of their castle of the sky, glorious tapestries woven of stars. All 48 constellations of the Northern Hemisphere were designed and named by the Greeks. The story of Andromeda is one such tapestry, woven of 7 constellations spread across the entire autumn sky. The story contains detailed astronomical observations preserved as highlights in the sky tapestry. It begins with the constellation Cassiopeia, queen of the oldest realm in Africa, Ethiopia. When the constellation Cassiopeia is on the horizon, it looks like a staircase going up to the Milky Way. Step pyramids around the world are often thought to have been inspired by the constellation Cassiopeia. In any case, Cassiopeia is a beautiful constellation, indicating that Queen Cassiopeia was also a beautiful woman. She was good-looking, but equally vain, which sets off all the dramatic action. Cassiopeia can be found in the night sky opposite Ursa Major from the North Star. Like Ursa Major, Cassiopeia circles the North Star and is a circumpolar constellation. A supernova was observed in Cassiopeia around 1680 Earth time. Cassiopeia A having occurred about 11,000 years earlier. The Chandra X-ray satellite recently recorded an extraordinary photograph of this supernova remnant showing the elements sulfur, calcium, silicon, and iron amid the expanding cloud's high-intensity X-rays. Cassiopeia's husband is also a circumpolar constellation, a minor dim one named Cepheus. He had his own kingdom. A merger of empires by way of marriage is something common throughout history. Cepheus was a king of Phoenicia. There were many kings of Phoenicia back in the days when Phoenicia was just a collection of city-states along the western shore of the Mediterranean Sea. Cepheus can be found in the area between Cassiopeia and the North Star. The constellation of Cepheus is important to astronomers. It's where Henrietta Swan Leavitt discovered variable stars that pulsed at regular intervals. The rate of pulsation of the star indicates the true brightness of the star and enables a sure measurement of the distance to the star. The discovery of Cepheid variable stars was a major breakthrough for early 20th century astronomy. Cepheus and Cassiopeia had a daughter, Andromeda, also a noted beauty, about whom all the fuss is. It seems that one day Cassiopeia was boasting about the beauty of her and her daughter Andromeda. "We are more beautiful than any other women in the whole wide world." Well, such pretension can be forgiven for a queen. But then Cassiopeia went further and stepped beyond all natural bounds. In fact, we are more beautiful than any of the Nereids. Well, the Nereids were Greek mythological sea nymphs, daughters of the ocean. Noted for their beauty and kindness to sailors, the Nereids, all 50 of them, took offense at being dissed by a mere mortal woman. Cassiopeia had to be punished for exceeding the bounds of the civil order. By her excessive vanity, Cassiopeia transgressed beyond the bounds of nature, for which an unnatural punishment was inflicted upon the entire kingdom of Ethiopia. A monster from the bottom of the ocean, the constellation Cetus, began to devastate the coastal villages of Ethiopia as well as Ethiopia's fishing ships. Fittingly, Cetus is a constellation of the southern celestial hemisphere. The fourth largest by area of all the constellations, Cetus swims in a dark part of the sky called the ocean, with only its head rising above the celestial equator. This part of the sky contains several water-themed constellations: Pisces, the fishes, Aquarius, the water-bearer, and Eridanus, the river. Over 50 exoplanets have been discovered in Cetus. You can bet the James Webb Space Telescope will have a field day analyzing the spectra of these planets' atmospheres, looking for signs of life. Meanwhile, Queen Cassiopeia and King Cepheus must do something about the monster devastating the shores of Ethiopia. They consult an oracle and make another trespass beyond the realm of reason and nature. Tell us, oracle, what can we do to stop the monster from ravaging our kingdom? This monster is not a normal affliction of nature. An offense was committed against the higher realms, and this is the punishment. The monster cannot be stopped by any normal means. Only a human sacrifice of the noblest being may placate the beast. One error compounds another. The noblest person in the kingdom, of course, is Princess Andromeda. According to the command of her father and the consent, or perhaps a suggestion of her mother, Andromeda is chained to a rock offshore. She is the human sacrifice that her parents hope will save the kingdom. Wow. Da-da-da-da! Here comes the Greek hero to save the day, stop the human sacrifice, and turn Cetus to stone. Perseus. Now, where is Perseus coming from? According to legend, the Hebrides. Perseus went to the Hebrides in pursuit of the Gorgon Medusa. The geological scope of this tapestry is incredible, from the Hebrides to the Red Sea. The Hebrides are an archipelago of mostly rocky islands off the western coast of Scotland. It was impossible to sail any further. The Hebrides were the absolute end of the world. Perseus didn't have to sail to the Hebrides. However, he flew on a pair of winged sandals. Hey, way to go, Perseus! Now, Medusa was one of the all-time baddies. One look at Medusa was so terrifying it would petrify you, literally turn you to stone. Perseus was in great danger. So, what did our hero do? Instead of looking at Medusa, Perseus used the scientific principle of reflection. He slew Medusa by seeing her reflected in his polished shield. In our sky tapestry, Perseus is portrayed holding up the severed head of Medusa. In the night sky, one eye in Medusa's head opens and closes and opens again. Arabic astronomers named the star Algol, the ghoul. Algol is an eclipsing double star. One star is bright, the other one, not that much. As the dimmer star orbits the bright star, it passes in front of the bright star, eclipsing it, and the eye closes. Since the dim star takes 2 days, 20 hours, and 49 minutes to orbit the bright star, the eye in Medusa's head opens every day and a half or so. The constellation of Perseus is immediately below Cassiopeia, and skywatchers quickly look to see if Algol is eclipsed, if Medusa's eye is open or closed. Perseus flew back from the Hebrides, accompanied by Pegasus, the winged horse. The central part of Pegasus is the Great Square, made up of 4 stars. As Earth goes around the Sun, the Great Square is right in the center of the night sky in autumn. In the summer triangle of Vega, Deneb, and Altair are in the middle of the night sky. In spring, it's Leo the lion, and in winter, it's Orion the hunter. These are the walls of the castle in the sky, and all have marvelous tapestries adorning them. The constellation of Andromeda shares a star named Alpheratz with Pegasus. It's one of the corners of the Great Square, so it appears Andromeda may be riding on Pegasus. Her crown, remember she is a princess, is floating nearby. M31, the Andromeda Galaxy. To see M31, cross the corners of the Great Square from the lowest star to the uppermost star, and then go a little further to see the Andromeda Galaxy. Be sure to peek at it from the corner of your eyes. It's called averted vision. The corners of your eyes are more sensitive to light, so you'll be able to see the huge spiral galaxy 2.5 million light-years away as a smudge of light 1.5 times wider than the full moon. Now, Perseus doesn't go in for human sacrifice, so he stops it and saves Andromeda by exposing Cetus to Medusa's gaze. And here we encounter the second eclipsing variable in our sky tapestry, Mira, the heart star of Cetus, the sea monster. Mira, from which we get the English word mirror, so fitting in a story about vain beauty, is an eclipsing double star. The dim star orbiting the bright star is a white dwarf, not bright enough to see with the unaided eye. The effect is that Cetus's heart shuts off. Mira is eclipsed and disappears. This cycle repeats itself every 332 days. Our fabulous star tapestry has the only 2 eclipsing binary stars visible to unaided eyes, the nearest spiral galaxy, and a hero that doesn't like human sacrifice and uses the scientific principle of reflection to thwart mythological monsters. Wow, I would hang that in my castle too. Just saying.
A powerful burst of gamma radiation lasted a mere half-second, but it released an enormous amount of energy. It was more than our sun would produce in 10 billion years. This brief flash lit up the whole sky. Afterward, a much softer and more long-lasting glow replaced it. Astronomers examined the phenomenon with X-ray, radio, optical, and infrared waves. It turned out that people had finally seen a newborn Magnetar for the first time ever. It was likely formed after 2 neutron stars had merged. It resulted in a kilonova, one of the brightest and largest stellar blasts. Its light finally reached our planet on May 22, 2020. Imagine a massive star, at least 5 times the mass of our sun, reaching the end of its life. It might be because it's run out of its nuclear fuel. If it happens, the star starts to cool off. The pressure inside drops, and the gravity starts to squeeze inward. And then, more than 1 million times the mass of our planet collapses within 15 seconds. It happens so fast that an enormous shock wave causes the outer part of the star to blow up. It produces a blinding burst of light. This powerful blast is called a supernova. What's left behind is an incredibly dense core with a huge cloud of hot gas, called a nebula, expanding around it. If the star has been massive enough, more than 10 times the size of the sun, it's likely to turn into a black hole. If not, it turns into a neutron star. It's basically a giant nucleus, the central part of an atom. These stars are mostly made up of neutrons and are rarely larger than 20 miles across. For comparison, our sun is almost 865,000 miles across, which is 109 Earths put side by side. But don't let this relatively tiny size fool you. Any neutron star is at least 1.5 times heavier than our sun and has an intense magnetic field. If you scooped just a teaspoon of this star's insides, this matter would weigh more than 1 billion tons. It's so dense that it makes neutron stars some of the most extreme objects people know about. The next stop is the black hole itself. When 2 neutron stars merge, they most often create a new, much heavier one. Within milliseconds, or even less, this star collapses into a black hole. But the astronomers who examined the flash of light recorded in March think there might be another outcome. They're almost sure they saw something never observed before: the birth of a Magnetar. That's a rare form of a neutron star with an ultra-strong magnetic field. It's 1,000 trillion times stronger than our planet's. This field is also so powerful, it heats the star's surface up to 18 million degrees Fahrenheit. To put it simply, Magnetars are the most powerful magnets in the universe. Their magnetic fields can seriously mess with the neighborhood. Atoms, unlucky enough to get close to such a star, get stretched into pencil-thin lines. If you somehow found yourself several hundred miles away from a Magnetar, it would end badly for you. The magnetic field would first disrupt your bioelectricity. It means that your nerve impulses wouldn't work anymore. Even your molecules would change under the influence of the star's field. In the end, you'd pretty much vanish. If a Magnetar flew within 100,000 miles from our planet, it would wipe out all the data on every single credit card in the world.
Locating the North Star is quite easy on a clear night. The only thing you need to do is find the Big Dipper. Those two stars on the end of the Dipper's cup point the way to the North Star. See? It's the tip of the handle of the Little Dipper, or the tail of the Little Bear. It's in the constellation Ursa Minor, over there. People have been watching the North Star for centuries. This bright star is also known as Polaris. It's situated almost directly over our planet's North Pole, which makes it a great landmark for a traveler without a compass, or a GPS on their smartphone. It's also Earth's closest Cepheid. That's what we call a star that pulses regularly in brightness and diameter. Polaris is also part of a binary system of two stars. It's got a dimmer sister. It's known as Polaris B. You can actually see it circling the North Stars from Earth. But the more astronomers watch Polaris, the less they understand. The problem is, no one can agree on how big or distant the star is. Scientists have several ways to estimate the mass, age, and distance of a star like Polaris. One method is called the stellar evolution method. After studying the brightness, color, and rate of pulsation of a star, experts use this data to figure out how big or bright it is, as well as what stage of life it's in. Once these details are clear, it's not hard to find out how far a star actually is. It's simple math once you know the luminosity of a star in real life and how dim it looks from our planet. Such models are especially precise for stars like Polaris because the rate of their pulsing is directly related to their brightness. This makes it easy to figure out the distance to any of those stars. Astronomers trust this method so much that Cepheids have become an important tool for measuring distances all across the universe. At the same time, there are other ways to study the North Star, and they don't agree with the stellar evolution models. Polaris is a so-called astrometric binary. It means you can see its companion going around it. It looks as if a circle is being drawn around the bigger star. To complete one orbit, the smaller star needs around 26 years. Even though astronomers haven't made detailed observations of Polaris B's full circuit, they've seen enough to know what its orbit looks like. Using this information, one can apply Newton's laws of gravity to calculate the masses of the two stars. Combined with the Hubble Space Telescope's new measurements, these calculations lead to very precise numbers. Polaris is supposed to be around 3.45 times the mass of the Sun, but that's much less than the mass you get from stellar evolution models. They suggest a value of almost 7 times the mass of the Sun. But there's another reason why this star system is weird. After calculating the ages of the stars, researchers concluded that Polaris B is much older than its bigger sibling, but it's extremely unusual for a binary system. Normally, both stars are of the same age. One explanation might be that at least one of the measurements is simply wrong. After all, Polaris is a difficult star to study. Since it's positioned above our planet's North Pole, it's outside the field of view of most telescopes. As for those telescopes that do have the needed equipment for measuring the star's properties precisely, they're typically used for studying much more distant and fainter stars. Polaris is simply too bright for such instruments. It blinds them. There's a theory that the main star of the Polaris system was once two stars, but they collided a few million years ago. Such a binary collision could rejuvenate stars by pulling in extra material and making the stars look as if they went through the fountain of youth. It would also explain some other oddities, since stars that appear as a result of binary collisions don't fit stellar evolution models. Unfortunately, so far, none of the theories have been confirmed. The North Star is actually a big deal. Earth is spinning non-stop, which causes the sun to rise and set and stars to travel across the sky. Our planet is also tilted. That's why we have seasons. If we drew a line through the axis Earth spins around and extended it over 300 light-years past the North Pole, at the end of that imaginary line, there would be the North Star. It stays almost exactly at the same spot in the sky at all times and always points the way north. It's really important for navigation. People heavily relied on it in the days before GPS. If you were standing on the equator, Polaris would be right at the horizon. At the North Pole, it would seem to be right over your head. In other words, using the star's height in the sky, you can not only figure out the needed direction, but also understand where you are on Earth. Curiously, there's no South Star. There isn't a bright enough star right above the South Pole, but one day we might get such a star. When you spin a top on the table, its end moves in a circle. We know this phenomenon as precession. Earth behaves in the same way, and the North and South Poles won't always point towards the same spots in the sky. In the next 26,000 years, it may cause the North Star to change from Polaris to a few other stars and back again. One day, the title of the North Star will go to Vega. It's the 5th brightest star in the night sky and the 2nd brightest in the northern celestial hemisphere. Vega has another name, Alpha Lyrae. That's because it's the main star of the Lyra constellation. Vega has been one of the most crucial stars to people since ancient times. It's very bright and blue, hence very recognizable. Vega was the North Star several thousand years ago, and it'll regain this status in 12,000 years or so. This star is located a mere 25 light-years from Earth. It's just 450 million years old, which makes it way younger than our own 4.6 billion-year-old star system. Astronomers study Vega to learn more about star systems in the early stages of their formation. Vega is almost directly overhead at mid-northern latitudes on a summer night. It hides behind the horizon for only 7 hours a day. You can see it on any night of the year. If you travel farther south, you'll find out that Vega lies below the horizon for longer periods of time. But in Alaska, northern Canada, and some parts of Europe, Vega never sets. Vega's blue-white light is bright enough to be featured a lot in ancient cultures, from the Chinese to the Polynesians to the Hindus. Vega's name can also be translated as falling or swooping. This is a reference to the times when people regarded this constellation as a swooping vulture, not a Lyre. Vega was also the first star to get photographed, other than the Sun, of course. To do it, astronomers at Harvard College Observatory used a 15-inch refractor, and it happened again in 1850. Around 2 decades later, an amateur astronomer broke down Vega's light to reveal various elements making up the star. In 2006, thanks to telescopic observations, scientists found out that Vega was whipping around so fast that its poles were several thousand degrees warmer than its equator. The star rotates every 12.5 hours and is at 90% of its critical rotation speed. That's the velocity at which an object can tear itself apart. In 2013, researchers announced that they had discovered an asteroid belt around Vega. It means there might be planets somewhere out there among space rocks. There are 2 areas, an outer region that contains icy asteroids and an inner region with warmer space rocks. Scientists can examine bright stars like Vega using NASA's mission called TESS, which stands for Transiting Exoplanet Survey Satellite. It was launched in 2018 to conduct an all-sky survey. The main goal of this mission is to search for exoplanets, but the satellite can also look for star variability. By examining such stars as Vega, TESS can help scientists learn more about the early stages of star evolution.
Have you ever wondered why all planets are perfectly round? And what if these celestial bodies decided to break the rules and change their shape? Would we end up with square planets, triangular moons, or maybe even intergalactic shapes we can't even imagine? Well, let's find out. So how do planets form in the first place? The universe is filled with swirling clouds of dust and gas. These clouds, called molecular clouds, consist of various elements and compounds such as hydrogen, helium, carbon, oxygen, and so on. They're like a cosmic kitchen filled with the ingredients needed to cook up some brand new planets. The first step in the recipe for planetary formation is called the accretion theory. Let's say that something happens that causes gravitational instability, like a supernova goes off nearby or something. This pushes the gas and dust in the cloud and causes them to come together. Because of gravity, these particles start falling toward a central point. They become more tightly packed together, like when you squeeze a ball in your hand. And eventually, they're squeezed so hard that the cloud starts to flatten into a disc shape. Kind of like when you mix flour and water to make pizza dough. This disk is called a protoplanetary disk. It's also spinning because the cloud's particles had some rotation to begin with. Now, imagine these tiny dust particles and gas molecules dancing around in the disk. Sometimes they bump into each other, and when they do, they stick together like Velcro. These little clumps of dust and gas are called planetesimals. They're the building blocks of planets. And as the planetesimals continued to collide and merge, they grew larger and larger, forming protoplanets. The protoplanets were getting serious about their size, and their gravity became stronger. Some of them got so massive that they became the grand masters of their cosmic neighborhoods, the planets we know and love. Each planet had its own unique recipe of gases, rocks, and sometimes even water. But why do the planets look like spheres? Well, it's all because of gravity. Let's go back to our protoplanets. Imagine you're squeezing a balloon with your hands. The air inside of the balloon pushes back, creating pressure. Something similar happens with planets. Gravity squeezes its material inward, pulling in towards the center. And since gravity acts equally in all directions, it pulls material from all sides toward the center of mass, resulting in a sphere-like shape. And that material pushes back with pressure, resisting the force of gravity. In the end, they both find a sweet spot where they balance each other out. It's called hydrostatic equilibrium, a fancy term that means everything inside a planet is in balance. But that's not all. Another thing that makes the planet spherical is their rotation. Think about a ball of Play-Doh or something like that. Imagine you spin it rapidly. The material starts to push outward, making the Play-Doh bulge at the equator and flatten at the poles. The same thing happens to planets. As they spin on their axes, the combination of gravity and rotation pushes the material outward, making the planet bulge at the equator. They low-key want to become disks again. However, gravity doesn't want any lumpy planets. It wants them to be nice and round, so it keeps pulling on the material, trying to make everything as compact as possible. Eventually, gravity wins, and the planet settles into a spherical shape. Let's take some examples from our planetary playlist. Jupiter, the giant of the solar system, loves to show off its oblateness. It spins so fast that it becomes noticeably squished at the poles and chubby in the middle. It's like a spinning top with a cute belly. Saturn, the ringed wonder, also joins the oblate party. It spins around with its beautiful rings, and its oblateness is even more pronounced than Jupiter's. These examples show how rotation can give planets a unique shape. They go from being perfectly round to having a delightful bulge around the middle. It's like cosmic pottery, where the spinning motion creates a playful and distinct shape. So now you know why the planets are round. But what's more interesting is, what if they weren't? What if they were, let's say, cubical, or even triangular? Well, let's see. A cube-shaped or a triangle-shaped planet would have its mass spread out in a completely different way than a sphere. And you know what that means? Gravity would be all shook up too. On a spherical planet, gravity pulls everything towards the center because the mass is evenly distributed around that center. But when we introduce a cube-shaped or triangle-shaped planet, things get interesting. If you're standing at the center of one of those faces, you'd feel the strongest pull of gravity. That's because the faces are the closest to the center of gravity. And as you venture away from the center and start walking towards the edges, gravity starts playing tricks on you. You would feel the struggle against the steep-angled gravity. Walking on those edges would feel just like climbing a mountain, or walking on a super steep slope. All because gravity wants you right in the middle of the face, and nowhere else. Now imagine the terrain along the edges and corners. It's a barren, rocky, and dry landscape. Why? Well, all the water would pool in at the center of each face, leaving the edges high and dry. And the air quality? Well, it's either non-existent or so thin that it can't support life. Not the coziest place to set up camp, that's for sure. And don't forget your warm clothes, lunch, and hiking boots. You'll need them because of the crazy climate. The type of climate you'll encounter on our cube or triangle-shaped Earth depends on how it spins. If it rotates at its corners, each side would enjoy a mild, temperate climate. However, if it rotates on an axis through two of its faces, things get intense. Picture a roller coaster version of our current climate. Some faces would be polar wonderlands, icy and chilly. The top and bottom faces for the cube, and the bottom face for the triangle. Meanwhile, the other sides would be completely different. In a cube, they would be scorching hot with an equatorial climate that would make you break a sweat. Instead of sunlight gently curving along the surface, it would directly beam onto these faces. Talk about feeling the heat. And on a triangular planet, the sunlight would strike the faces at an angle. This angled sunlight would create fascinating temperature variations across the planet. Imagine this. As you move from the base of the triangle towards the tip, the temperatures would gradually decrease. The base, where the sunlight hits most directly, would be the hottest region, just like the equatorial climate we're familiar with on our spherical Earth. But as you venture towards the tip, the angle of sunlight would be less direct, leading to cooler temperatures. But the base is still super cold and dark, since the sunlight doesn't directly reach it. So the triangle would be absolutely crazy in terms of temperature changes and climate zones. By the way, you know that cozy blanket of air we call the atmosphere? Well, on our angular Earth, things would get a little topsy-turvy. Gravity would be pulling stronger from the center of each face. The result? The atmosphere would go through some crazy changes. Picture this. At the center of each face, where gravity is strongest, the atmosphere would gather and thicken. It would be like a bustling city, full of air molecules. But as you venture towards the edges, things would start to thin out. The atmosphere would become scarce and very thin. So breathing along the edges would be quite a challenge, and the edges would be a tough neighborhood for life to thrive. Moreover, a thinner atmosphere means less protection from the sun's radiation and solar winds, so corners and edges would be extremely dangerous for humans. Of course, this is all just a playful exploration of what could be. Our Earth loves its spherical shape, and that's a good thing. But there's no harm in imagining wild and wonderful possibilities, so keep your imagination soaring and continue to marvel at the marvels of our amazing planet, however it may be shaped.
Now, Jupiter used to be flat and look like an M&M candy. Now I'm hungry. And it wasn't the only flat pattern in our solar system. Turns out there are tons of things that can go wrong during a planet's formation, like locking up to the sun or getting whooshed into open space. Let's check it out. The Earth isn't flat, but Jupiter might have been. Instead of being a big round ball, gas giants in our system might have started more like flat pancakes. Jupiter is one of the oldest of our neighbors. It's 4.6 billion years old, just like our Sun. And when it was just a baby planet, it likely formed through a process called disk instability. It all begins with stars. When a star is forming, it doesn't look like a round object. It's more like a big disk of stuff. During this stage, really hot winds made of charged particles blow out. The dust in that disk contains stuff like carbon and iron. Some of them collide and stick together, forming bigger objects. Dust turns into pebbles, pebbles turn into rocks, and rocks bump into each other, getting bigger. Gas in the disks helps all these solid bits stick together. Some break apart, but others stick around, and they're the ones that become the basic pieces of planets. They're called planetesimals. Even gas giants like Jupiter started off as tiny specks of dust, smaller than a human hair. Eventually, they formed their own big ring-shaped disks of gas. They began to spin around our Sun, growing bigger by gathering gas and rocks like snowballs. Gas giants are special. They were born from the colder parts of the disk. In cold areas, molecules are slower, which makes them easier to grab. In these places, water could freeze, and tiny ice pieces stick together and are mixed with dust. These dirty snowballs gather up and then form cores of huge planets, like Jupiter, Saturn, Uranus, and Neptune. In the warmer areas closer to the star, rocky planets like Mercury, Venus, Earth, and Mars start to form. After the icy giants were born, there wasn't much gas left for these smaller planets. It might take tens of millions of years for these rocky planets to form after the star is born. And our Sun was growing at the same time, sucking up nearby gas and pushing faraway stuff even farther out. After billions of years, the disk changed completely, turning into a round star with a bunch of planets, dwarf planets, asteroids, moons, meteoroids, and comets around it. Recently, simulations showed that these protoplanets, as these early dust balls are called, don't start off looking like the planets we know. In the case of gas giants like Jupiter, they look more like squashed balls or M&M's candies, not the peanut kind. When the Sun was young, the disk of gas and dust surrounding it cooled down and became unstable. It started breaking into big chunks. These chunks dramatically collapsed together under huge gravity to create Jupiter. It became a round gas giant over time. There are a lot of oddities that can happen during that process of planet formation. Ever wonder why Venus or Uranus spin in the opposite way compared to other planets? Usually, when things form from a spinning disk of gas, they tend to spin in the same direction. For example, if you spin a bunch of balls on a string, they all twirl in the same way. So, theoretically, all planets should spin in the same direction too. But there are a lot of fast-moving objects like comets and asteroids in our solar system. When they smash into planets, especially during their early days, this collision might send the planets to spin in the opposite direction. Venus and Uranus probably survived a massive collision. Luckily, they weren't repelled to outer space. The gravity from the Sun and nearby planets pulled them back into place. There are also so-called tidally locked planets. These are celestial bodies that spin in a way where one side always faces their star, while the other side remains in perpetual darkness. So, one side is always very hot, while the other is extremely cold. If we were on a planet like that, we would only be able to live on a thin line in between. These planets form when they're very close to their star. The gravitational forces are extremely strong, and over time, these forces slow down the planet's rotation until it matches the time it takes to orbit the star. Imagine you're spinning in your chair. Someone comes up to you and, holding onto your chair with their hands, starts spinning with you. This way, you'll always face each other. Tidally locked planets kind of work like that. Our moon is tidally locked to our Earth, which is why we only see one side of it. We've discovered more than 5,000 planets outside of our solar system called exoplanets. Some of them have very strange orbits. For example, planets with incredibly long orbits, thousands of years to make one trip around the star, or very wonky, comet-like orbits, or so-called hot Jupiters. They're super close to their star, way closer than Mercury is to our Sun. But these planets couldn't have formed where they are now. As their solar system evolved, they changed their positions for some reason. This rearranging is called planetary migration. There are three main ways this migration happens. First, because of the gas and dust spinning around the planet. When a planet is bumping into this stuff, it can create spiral patterns in the gas. These patterns can either push the planet closer to the center or farther away, depending on how they mix together. It's called a gas-driven migration. This is what Jupiter experienced when it moved closer to the Sun billions of years ago. I wasn't around then. This also explains the existence of hot Jupiters. Second, big planets can shove the smaller ones, changing their paths. Third, the star's gravity can tug on the planet, making its orbit more circular. Ever heard of rogue planets? Imagine a lonely planet floating in the vastness of space without a star to call home. They're like the wandering nomads of our galaxy, doomed to drift around forever. And there are so many of them, there might be more free-floating planets than ones that are tied to stars. We're talking trillions of rogue planets hanging out in our Milky Way galaxy alone. They're often as massive as our biggest planet, Jupiter, but most of them might be Earth-sized. Some might even have thick atmospheres that keep them warm, even though they're far from any star. Some of them might have wild auroras, while others could host moons with liquid water, a potential haven for life. There's even a chance that they might contain extraterrestrial life. These planets might bump into other stars or even entire planetary systems as they journey through space. Sometimes they might get caught in a star's gravity for a while before getting flung back out into space. But how are they born? Sometimes, during this chaotic process of planet formation, not all planets can manage to stay close to their parent stars. Some of them get kicked out of their solar systems due to powerful gravitational interactions with other planets or passing stars. These ejected planets become rogue planets. In 2012, astronomers found a solar system from the very beginning of the universe. This system included a star and 2 planets. We called it a fossil system. The star is super old, about 13 billion years, almost as old as our entire universe. It was mostly made of just hydrogen and helium. This is unusual because planets usually form from clouds of gas that contain heavier stuff. That's when we figured out that the way planets formed before was different from how they form now. We know that stars with more metals are more likely to have planets. In astronomy lingo, metals means any chemical element other than hydrogen and helium. But in the early universe, there weren't many metals. Most of them were created inside stars and then spread out into space when those stars blew up. So, when did the very first planets form? This newly discovered system helps answer these questions. Its 2 giant planets are orbiting a star that's incredibly low in metals and extremely old. This should be really rare, if not impossible, but they exist. This means that maybe there are more planets in metal-poor systems than we thought. Studying them will help us learn more about the history of planet formation. Uranus has a 22-year-long winter. On a planet like that, if it was habitable, everything would be frozen and covered in ice, white and gray desert all around. People would have to stock up on food and supplies, make extra sturdy buildings and homes, and always wear thick, warm clothes. Finally, transportation would be next to impossible. But thanks to the Sun, each planet in our solar system has unique weather, climate, and seasons. There are several reasons contributing to that. First of all, it's all about how far a planet is from the Sun. If a planet is close, like our neighbor Mercury, it gets a severe sunbath. But if it's far away, like the dwarf planet Pluto, it gets frigid even during summer. Now, think about how fast a planet spins. Planets that take their sweet time to rotate, like Mercury, have super long days and nights. That means one side gets toasty hot when the sun's out and freezing cold when it's dark. Earth is pretty balanced with its moderate spin speed. The atmosphere matters too. A thick atmosphere keeps temperatures from going wild. But if there's almost no atmosphere, things heat up and cool down immensely. The tilt of a planet's axis and the orbit shape are crucial as well. Even on Earth, places near the poles get 6 months of daylight and 6 months of night. And if a planet's path around the Sun is like an oval, it heats up and cools down more than it moves. Now, no 2 planets are unique. While some have these changes, others don't. Let's start with Mars, our favorite little planet and potentially our future home. It's the 4th wheel in our solar system and has a quirky way of doing seasons. Like Earth, it has 4 of them, although they're roughly twice as long as those on Earth. But this planet has an eccentric egg-shaped orbit. Because of this, its orbital speed varies more. This influences these seasons. Martian winters last about 4 Earth months. They're also much colder than on Earth. Near the poles in winter, temperatures can get down to minus 190 degrees Fahrenheit. One hemisphere grows an ice cap as winter rolls in, snatching about a quarter of the atmosphere as dry ice. Then, in spring, it gives it back. Mars also doesn't have the luxury of massive oceans like Earth to balance out its extreme temperatures. Scientists believe it might have had some of that in its early days, but now all the water is gone. With no water, Mars can hit very low temperatures in winter and hotter summer days. The grand gas giant Saturn has a slightly more tilted axis than Earth. However, despite its elliptical path and tilt, it stays consistently chilly. That's because it's way out there, far from the sun's warmth. Even though it's summer, Saturn remains distant and doesn't get too cozy. It also has a thick atmosphere. The atmosphere on a planet acts like a temperature regulator. If some part gets too hot or cold, the atmosphere gently distributes this temperature across the planet. So, while one side might catch more sunlight during its equinox, the thick air ensures things stay relatively cool. Up high in Saturn's atmosphere, though, it's a different story. Temperatures can swing from seriously chilly in summer to an almost absurd -312 degrees Fahrenheit in winter. Uranus is the next planet, the ice giant. With an elliptical orbit and a serious distance from the Sun, it's stuck in a perpetual deep freeze. Its thick atmosphere also keeps temperatures frosty throughout the year. Uranus has a wild tilt, 3 times bigger than Earth's. It's almost lying on its side, and is probably one of the most intense places in our solar system. During Uranus's summer, one pole gets full sun, while the other end faces the deep chill of darkness. In fact, because of its weird tilt and rotation, Uranus is even colder than its more distant neighbor, Neptune. As we mentioned, each season on Uranus lasts around 22 Earth years. That's as close as we get to George Martin's fantasy books. That's because Uranus takes a leisurely 84 years to complete one path around the Sun, so its journey through the year is very slow. The final planet in our solar system is Neptune. It's the most faraway icy giant. It has a tilt almost the same as Earth's and a nearly circular orbit, so it feels like it's supposed to be a bit more balanced. However, this planet maintains a bone-chilling atmosphere with unimaginably low temperatures. That's because Neptune receives only a tiny 0.1% of the sunlight Earth enjoys. On Earth, there's a gradual temperature shift from near to far. On Neptune, because of its circular orbit, there's only one atmosphere taking a spotlight. Unlike its neighbor Uranus, Neptune gets a bit of warmth from its core. But this warmth doesn't help much. The cold is pretty consistent, whether it's winter or summer. But some planets don't bother with traditional seasons. They just imitate them by having different temperature cycles throughout the year. These planets include Mercury, Venus, Mars, and Jupiter. Mercury is the closest planet to the Sun. Mercury is very weird, because one full day-night cycle on that planet equals 176 Earth days. After half a year on Earth, it's finally time for Mercury people to go back home from work. That's because it moves in an egg path. This is also the reason why it has some wild temperature changes. Sometimes it's very close to the Sun, sometimes it's not. At the same time, it has no atmosphere and no protection from the Sun. This results in extremely hot days and extremely cold nights. But that means it has plenty of time to go from scorching hot to freezing cold. When it's farthest, that's Mercury's true winter, or at least how we call it. So if it had seasons, there would only be 2. The next planet is Venus. It's a planet of relentless heat. Forget about seasons. It's just plain hot there all the time. It's super close to the Sun, and its almost circular orbit and tiny tilt of 3 degrees mean temperatures stay pretty steady throughout the year. Even in the supposed winter or the middle of the night, the temperature doesn't dip below 820 degrees Fahrenheit. It also decided to have a weird spin. Venus spins in the same direction as it moves around the Sun. That means the Sun is always right overhead, pouring its entire fiery love on the planet's surface. Venus doesn't really do the seasons like Earth. The closest they have to seasons is 225 days with at least 4 hours of sunlight. This you could call Venus's version of spring and fall. Jupiter, the big guy in our solar system, doesn't bother with the whole seasons drama. It keeps things simple with a tiny tilt of 3 degrees, almost as laid back as Mercury. Plus, its orbit is a close match to a perfect circle, so it doesn't have much variation in sunlight. Also, with a speedy rotation of less than 10 Earth hours, there's no time for the appearance of seasons from long nights. Winter on Jupiter is basically a repeat of any other time of the year. And finally, Pluto, which is still not a planet, but still worth looking at. Pluto resides on the outskirts of our solar system. This little outcast is the definition of cold. The temperatures are around -380 degrees Fahrenheit. It has the weirdest orbit, too. Its orbit is very long, elliptical, and tilted. Pluto travels a huge distance from the Sun. That, together with an almost non-existent atmosphere, keeps Pluto in a perpetual cold state. Winters there can get a bit more extreme than average. However, the biggest shift someone stranded on Pluto would notice isn't the temperature, but the Sun's brightness. Always thousands of times fainter than our earthly view.
Look at this fascinating planet. It looks as if it's burning. It must be hotter on its surface than in the middle of Death Valley. The ground is parched, cut by giant cracks. There's not a drop of water in this boiling world. Now, it's the same planet, but it looks like a totally different place. Everything is frozen. The temperatures are so low, there isn't even a tiniest chance that life could survive on this planet. This bizarre world is called HD 20794d, and it's located 19.7 light-years away from Earth in the constellation Eridanus. This planet is a super-Earth. This term means that it is larger than Earth but smaller than such ice giants as Neptune. What makes this planet especially interesting is its unusual orbit, which moves it in and out of its star's habitable zone, the region where temperatures might allow liquid water to exist. Now, we haven't seen this unusual planet directly. Astronomers detected it by measuring tiny wobbles in its star using two powerful instruments, espresso and HARPS, located at telescopes in Chile. These instruments measure radial velocity, which is the small movement a star makes as a planet's gravity tugs on it. The larger the wobble, the more massive the planet. Later, astronomers analyzed the data and figured out that the planet in question has a mass around 6 times greater than Earth's. It orbits a star, which is slightly smaller and dimmer than our Sun. What makes this star unique is that it is bright enough to be seen with the unaided eye, unlike many other stars that host exoplanets. You won't be able to see them without a telescope. The star system has been observed for over 20 years. Astronomers have long suspected it had multiple planets. In 2011, scientists discovered 2 other super-Earths orbiting the star every 18.3 and 89.6 days, respectively. For some time, researchers thought they had found a third planet with an orbital period of 40 days. Later, they realized they had made a mistake. But recently, after reanalyzing years of data, astronomers have confirmed that the third planet does exist, and it's our extreme HD 20794d. A researcher from the University of Oxford played a key role in identifying the planet. He used a special computer algorithm called Yarara to separate the planet's weak signal from the background noise. It helped him confirm that the planet truly existed and was pretty unique. Unlike the planets in our solar system, which have mostly circular orbits, the newly discovered one follows a highly elliptical, stretched-out orbit. It takes 647 days to complete one trip around its star. That's just 40 days shorter than Mars's orbit around the Sun. At its furthest point, the planet is twice the Earth-Sun distance, which makes it an icy world far outside the habitable zone. At its closest point, it moves inward to 0.75 AU, where it enters the habitable zone, where liquid water might exist. This extreme movement creates truly bizarre seasons. For some part of its orbit, HD 20794d is frozen, like an icy wasteland. As it approaches its star, temperatures rise and ice likely melts, forming temporary oceans. The planet then experiences a short, scorching summer. It is so hot that the water on its surface might evaporate into the atmosphere. Shortly after, the planet moves away again. It triggers a gloomy fall with rains, followed by a deep freeze in winter. In other words, the planet switches between extreme cold and intense heat, which makes it a very unpredictable place for life. If any life forms exist there, they certainly need to adapt to dramatic changes in temperature and environment. Why does the planet follow such a mind-boggling orbit? It might be a leftover effect from events billions of years ago, when the planetary system was still forming. At some point, another large planet may have disturbed the orbit of our extraordinary friend. Another possible explanation is that a giant planet once existed in the system, and its gravity pushed HD 20794d into an elongated path. Later, this giant planet may have been ejected from the system, leaving the smaller planet in its current orbit. This theory makes sense because the two other planets in the system, B and C, have more normal circular orbits. The discovery of this planet is so exciting because it challenges what we know about habitable planets. Most planets in the habitable zone stay there permanently, but HD 20794d only passes through it. Scientists want to know if such a planet could still support life, even briefly. So future telescopes will study the atmosphere of this planet, looking for signs of water, gases, or even life. Another super-Earth that might have the right conditions for life orbits a star 137 light-years away. In space terms, this is considered relatively close. A light-year is around 6 trillion miles. The planet is called TOI 715b, and it's about 1.5 times the size of Earth. Unlike HD 20794d, it's permanently located in the habitable zone. Look, that's what astronomers think the planet might look like. TOI 715b orbits its star very quickly, completing a full orbit in just 19 days. But even though it's close to its star, it may not be extremely hot, all because its star is a red dwarf. That's a type of star that is smaller and cooler than our Sun. This means TOI 715b could have a milder temperature compared to other exoplanets that orbit closer to hotter stars. NASA discovered the planet using the Transiting Exoplanet Survey satellite. This space telescope finds planets by watching for small dips in a star's brightness, which happen when a planet passes in front of it. Since red dwarfs are smaller and dimmer than the Sun, planets passing in front of them are easier to detect. Astronomers are planning to study the planet further using the James Webb Space Telescope. This powerful telescope, located 1 million miles away from Earth, can analyze the atmospheres of distant planets. If TOI 715b has an atmosphere, JWST could help scientists determine what gases are present in it and whether such conditions could support liquid water or even life. One more promising world for our search for extraterrestrial life is an extremely dense super-Earth in the K2360 system. An international team of researchers from Japan and Europe has discovered this remarkable multi-planet system orbiting a Sun-like star located 750 light-years away. This system has 2 planets, including one of the densest rocky planets ever found. The K2360b is a rocky super-Earth, about 1.6 times the size of Earth, but with a mass 7.7 times greater. This makes it as dense as lead. The planet orbits its star incredibly fast, completing one full orbit in just 21 hours. It's the densest known ultra-short period planet with well-measured properties. As for its sibling, this is a much larger outer planet with at least 15 Earth masses. It takes 9.8 days to orbit its star. Sadly, since it does not pass in front of its star from our viewpoint, scientists cannot determine its exact size. The unusually dense planet might be the core of a much larger planet. Over time, intense radiation from its parent star may have blown away its outer layers, leaving behind only its dense, rocky core. So, in fact, this planet could show us what might happen to some planets that are too close to their stars. Astronomers think that the planet may have moved inward over time due to interactions with its larger companion planet. One possibility is high eccentricity migration, where a planet's orbit becomes highly stretched out due to gravitational interactions before gradually becoming more circular near the star. Another theory is that the planet's spin and axial tilt can cause its orbit to become more circular. Such planets are rare, and finding one with a massive outer companion can help scientists refine their theories about how planets form and evolve in extreme environments. With its help, we might also understand how rocky planets evolve and what happens to planets that get too close to their stars.
Very recently, astronomers have found 3 potential super-Earth planets orbiting a somewhat close orange dwarf star. The term super-Earth is used to describe a planet beyond the solar system with a mass higher than that of Earth but below those of the ice giants of the solar system, Uranus and Neptune. An international team of researchers, led by Dr. Shweta Dalal from the University of Exeter, found that the exoplanets were orbiting star HD 48498, which is located around 55 light-years away from Earth. The planets travel around their star in 7, 38, and 151 Earth days, respectively. The study describing these findings appeared in the journal MinRes on the 24th of June 2024. The coolest thing here is that the outermost exoplanet candidate orbits in the habitable zone of its host star, and the conditions there might be comfortable enough for liquid water to exist on the surface without boiling or freezing. Such habitable regions around stars are also known as the Goldilocks zone and are believed to be ideal for potentially supporting life. Another reason this discovery is so important is that the orange host star is like our Sun. But since it's an orange dwarf, it produces less radiation than our yellow dwarf star. It's also the closest planetary system to host a super-Earth in the habitable zone of a Sun-like star, which makes this discovery super exciting. It can help us move forward in our quest to locate habitable planets around solar-type stars. Who knows? Maybe this planet will be our new home one day. These potential super-Earths were detected thanks to the HARPS and Rocky Planet Search Program. Throughout a decade, the team taking part in this research has collected nearly 190 high-precision measurements using special equipment. By analyzing the spectrum of light coming from a star, astronomers can figure out whether it's moving toward us, this is known as blue shift, or away from us, that's what we call red shift. And still, to make sure their findings were correct, the team used lots of different methods and comparative analysis. Everything confirmed their conclusions. There indeed are 3 planetary candidates with minimum masses ranging from 5 to 11 times the mass of our home planet. The team also believes that the proximity of the star, together with the outermost planet's favorable orbit, can make this system a great target for future studies. Hopefully, further research will open doors for our understanding of planetary systems and the potential of life outside our solar system. Scientists have already discovered more than 5,000 exoplanets, which are planets outside the solar system, since the first such world was confirmed orbiting a Sun-like star in 1995. To find those distant planets, astronomers use different equipment, like NASA's Kepler Space Telescope, launched in 2009. Its mission was to find as many Earth-like planets dwelling in the Milky Way galaxy as possible. But it's not the only instrument used for searching exoplanets. Anyway, now let's look at the most exciting and promising of these worlds. Gliese 667 cc is a mere 22 light-years from Earth. But even though it seems close, it's still around 129 trillion miles away from us. The planet itself is around 3.8 times as massive as Earth and completes one orbit around its host star within 28 days. In other words, a year on that Earth-like planet is 13 times shorter than a year on our planet. Luckily, the star is a cool red dwarf, so the exoplanet most likely lies in its habitable zone. But there's still a chance that this world might be regularly baked by the flares coming from its parent star, which is not cool on many different levels. Kepler 22b is way further away than the previous world, more than 600 light-years away from our planet. It was the very first Kepler planet found in the habitable zone of its star. This world is larger than Earth. It's about 2.4 times our planet size. Sadly, we still don't know whether this planet is rocky, liquid, or gaseous. The orbit of Kepler 22b is similar to Earth's. It takes the planet 290 days to orbit its G-class star, which is kind of like our Sun. But this star is smaller and colder than ours. Another Kepler planet, this time it's Kepler 69c. It lies a whopping 2,700 light-years away from us. This world is also almost 70% larger than Earth. Researchers know nothing about its composition, but they found out that the planet needs 240 days to complete one orbit. This makes its position in its system like that of Venus in our solar system. At the same time, This world might be more habitable than Venus since its host star is a bit less luminous, 80% of our Sun. TOI 733b is a recently discovered world. It was found in 2023. It's out there, 245 light-years away from Earth, and needs just 4.9 Earth days to complete an orbit around its star. But the coolest thing about this planet is that it might have a massive ocean. According to scientists, the planet is likely to be completely covered with water. Does that mean there could be life on the super-Earth? Time will tell. GJ1214b is located 48 light-years from Earth. This planet is a super-Earth, almost 3 times bigger in diameter and 8 times heavier than our home. It orbits around its red dwarf star faster than you can binge-watch your favorite series, finishing a complete loop every 38 hours. But it's not just the planet's size or orbit that's out of this world. It's pretty hot out there, with mind-melting 450 degrees Fahrenheit. But the coolest thing is that this planet is practically drowning in water. The sizzling temperatures and crazy high pressures on JG1214b create some cool materials like hot ice and superfluid water. Superfluidity is something that happens in liquid helium when it's almost as cold as it can get. On Earth, water totally missed the memo about being superfluid because it needs ridiculously low temperatures and off-the-chart pressures to pull off that trick. Still, there's not much use in superfluid water. Even if you try it, you'll just get dehydrated. The super-Earth that's closest to us was discovered in 2016, and it's called Proxima Centauri b. It's located a mere 4 light-years away from Earth and has a mass remarkably similar to that of our planet. A year on Proxima Centauri b is short. It only takes the planet 11.2 days to complete a circle around its central star. Scientists discovered this world after they noticed that its parent star was slightly wobbling. They hadn't been sure what exactly had been happening there until they realized Proxima Centauri b's gravity probably produced pulls and tugs that caused these wobbles. Although the exoplanet is traveling in the habitable zone of its star, Proxima Centauri, it is exposed to extreme ultraviolet radiation, all because it lies very close to its parent star. Also, none of the telescopes that are currently working and exploring exoplanets are positioned well enough to capture the light from the atmosphere of this super-Earth. Most things there are still a mystery to us, even though we're talking about a planet that's really close. Super-Earth TOI 715b orbits a red dwarf, a star smaller and cooler than our Sun. At the moment, such stars remain prime candidates for finding habitable planets orbiting them. Those miniature rocky worlds have far closer orbits than those circling around stars like our Sun. But since red dwarfs are small and cool, the planets don't risk anything when crowding closer. They're still safely within a star's habitable zone. Experts say that TOI 715b might have once had an atmosphere thicker than that of Neptune, and now the planet could be in a transition state where it's losing its atmosphere. To confirm this suspicion, scientists need to do more research, and they might finally learn whether this planet is a watery terrestrial planet. So, Mars has several faces. No, really. Back in 1976, when the Viking 1 orbiter was checking out the red planet, it spotted something interesting, a big structure that looked like a human face. It was in the region called Cydonia. It soon became very popular. A bit later, we also discovered the so-called crown face in Libya Montes. Mars in general has a lot of strange structures on it. In 2022, we spotted a door-like structure there. NASA's Curiosity rover snapped some pictures of a rocky mound called East Cliffs on Mount Sharp. This mound has natural cracks in it, and one of them is about the size of a dog door, like something from an ancient Egyptian tomb. A lot of people hyped that story up. The image was shared widely on social media, making the crack look bigger than it really is. Some people think that it's hinting at extraterrestrial life. But after looking closely, NASA found out that it was just a narrow crack in the rocky terrain. These cracks and gaps are pretty normal in rocky areas, both on Earth and Mars. The crack formed naturally over time, maybe from wind erosion or Mars quakes. Mars is a gold mine of mysterious structures. Recently, we found some strange spiral shapes there. These are giant coils made of lava, and they look like big springs or loops. For years, we weren't sure whether Martian valleys were formed by lava or ice. These lava coils are shedding light on that mystery. Now, thanks to higher resolution images from NASA's Mars Reconnaissance Orbiter, researchers have spotted 269 lava spirals that can't be explained by ice-related activities. What's fascinating is these lava coils are like the ones we see on Earth, like those formed by Hawaiian lava flows. These spirals are so well preserved that they were easily overlooked before. They range from 16 to almost 100 feet wide and are subtle, blending into the dusty Martian landscape. These coils can teach us a lot about Mars's composition, especially its crust and mantle. We still don't know much about those. But Mars isn't the only planet with strange structures on it. For example, Saturn, the gas giant of our solar system, has a fascinating feature at its north pole, a huge hexagon. This is a hexagon-shaped cloud pattern that's about 9,000 miles long, making it larger than the diameter of Earth. It's thought to be a jet stream made of gases moving very fast, at about 200 miles per hour. This hexagon was first spotted by the Voyager mission in the 80s, and later seen up close by the Cassini mission in 2006. The Cassini mission noticed a change in its color from blue to golden over time. There are different ideas about why Saturn has this thing. One theory suggests it forms because of the way winds move at different speeds near Saturn's poles. Similar shapes were created in lab experiments when liquids were rotated at different speeds. Another idea suggests that a slow spinning stream of air, along with Saturn's special weather patterns, might be responsible. In 2020, we found that when storms are surrounded by winds swirling in the opposite direction, they can create a steady hexagon shape. So far, this is the most likely explanation. Saturn also got lucky with the bizarre moons. One of them is called Lapidus. This moon has a weird feature, a huge ridge that wraps around its middle like a giant belt. This basically makes it look like a giant walnut. Where's my nutcracker? This ridge is incredibly tall by our standards, around 8 up to 12 miles high and stretching 124 miles wide. It covers more than 3/4 of the moon's surface and is considered the third largest mountain range in the entire solar system. Now, we don't have a clue about how this enormous ridge formed. It's unlike anything seen on other planets or moons. There's one idea, though. The ridge might be the remnants of a dead moon. Let's say billions of years ago, a colossal impact shattered chunks of material off Lapidus. These pieces circled around the moon, forming a mini-moon or sub-satellite. And over time, the gravitational pull of Lapidus tore this mini-moon apart, creating a ring of debris around it. As the debris from this ring fell back onto Lapidus, it built up the massive ridge we see today. They think this process happened quickly, maybe over centuries. Saturn's gravity didn't interfere because, luckily, Lapidus was quite far away from it. If Lapidus was closer to Saturn, its moon might have been pulled away. But we do need more simulations to see if this theory is true. Titan, another one of Saturn's moons, also has some weird stuff going on in its methane seas. Scientists have spotted these strange bright spots called magic islands that seem to pop up and disappear over time. We have no idea what they are. Titan's atmosphere is packed with complex organic molecules that clump together and fall to its surface like snow. These magic islands might be snow clumps that soak up methane and sink very slowly. But there's a problem. In water, molecules stick together, which is why stuff can float on top of it. But methane is different. It likes to grab onto other molecules, so it makes any solid thing sink immediately. Yet, these magic islands don't sink. There's a theory that these islands might be like sponges made of ice with lots of holes. When pieces of this holy ice come loose from the edge of the lake, they can float on Titan's seas for a bit before going down under. There are also other ideas, like bubbles of nitrogen gas or waves caused by wind. We need more research to know for sure. Moons like to be weird. Just look at our own one. In 1971, we found a patch with missing soil on our moon, and it looks like a blue lake. They call this mysterious spot Ina. We first spotted it during the Apollo 15 mission in 1971. Later, the Apollo 17 mission took clearer pictures of it. This spot, shaped like a bluish D letter, is one of the weirdest things on the moon. The color comes from special rocks rich in titanium called basalts. These rocks cover Ina's floor and make it look blue. There are also bluish areas near the edges of the mounds inside Ina. Ina is unique and probably has a long history. It might have had volcanic activity, with mounds that are about 3.5 billion years old. It's similar to the surface age of the volcanic field that surrounds Ina. Now, our moon has its own face, just like those on Mars. There's an area near the moon's south pole that looks like a face, but it's just a bunch of craters and shadows that happen to make an image resembling a face when seen from far away. These craters have been there for billions of years and cover about 16% of the moon's surface. Some of these craters might even have water and ice inside of them. You might be wondering why there are so many faces in our solar system. Well, that's because our brains are wired to recognize faces, even when there aren't any. It's a phenomenon called pareidolia. Our brains try to make sense of shapes, so when we see something that looks a bit like a human, our brain turns it into one because it's familiar. Like when you see a shadow figure on a chair with clothes, or even on Mercury. Some people see shapes like Mickey Mouse. So don't worry, it's not extraterrestrial life. It's our brains that play tricks on us, making us see familiar shapes like faces even where they don't really exist. This planet, the one right here, shouldn't exist, but it does. A newly discovered planet rotates around a star that's much smaller and dimmer than our Sun. The planet, however, is enormous. Such a tiny star couldn't create it, so it's like finding an ostrich egg in a chicken coop. A team at Penn State built a special tool called the Habitable Zone Planet Finder. It's an instrument that's supposed to find planets around dim, cool stars. It's connected to a big telescope in Texas. The tool looks at the light from these stars, which is mostly in the near-infrared, beyond what our eyes can see. This gadget can spot changes in a star's speed caused by a planet. If the star movement slightly changes, that means there must be a gravitational pull nearby. Years ago, this technique helped find the first known exoplanet around a star like our Sun. Today, we've improved this method to make more precise measurements. Our main goal is to find Earth-like planets. They should be rocky and located in habitable zones, areas around stars where liquid water could exist. The Doppler technique isn't that great at finding Earth-like worlds yet, but works well for cool, dim stars. And that's how we discovered the impossible LHS 3154b. Planets usually form in disks made of gas and dust in space. Picture a flat, spinning cloud of tiny particles. These particles come together and stick to each other, creating a flat, rotating disk. Over time, these tiny bits combine to form a solid core. This is the starting point for a planet. Once the core is there, it attracts more dust and even gas like hydrogen and helium. But making a planet this way isn't easy. They need a lot of stuff, mass, and materials. This process is called core accretion. Stars are a huge help in that process. Usually, big stars have more gravity, so they can gather more stuff to form planets. But the star we discovered recently isn't very big. It's 9 times smaller than our Sun. A star this small shouldn't have a big enough disk to make a heavy planet. To do that, its disk should have been at least 10 times bigger. But this heavy planet, LHS 3154b, exists. Now, this mysterious planet is 13 times heavier than our Earth. It's similar in size to Neptune. It's about 50 light-years away from us in the Hercules constellation, which, in space terms, is very close. The planet is also super close to its star, completing 1 year in almost 4 days. This discovery is making scientists rethink their ideas about how planets and stars come into existence. There are new theories coming around. For example, a theory called gravitational instability. It says that, instead of the pieces coming together bit by bit, the material in the disk collapses all at once, directly creating a planet. But even with this theory, it's hard to explain how such a heavy planet could form without a really massive disk. It'll take us some time to figure out the truth. This isn't the first planet that makes us doubt our theories. Recently, scientists found another planet called Hala. This planet is orbiting a star called Beetlejuice, and just like the previous one, it shouldn't really exist. It's way too close to its star. Stars change a lot during their lives. Normally, when a star becomes big and prepares to leave this world, it's called the red giant stage. A star like that tends to destroy or push away any nearby planets, creating a huge mess. Hala rotates around a red giant, and it should have been swallowed or destroyed by the expanding star a long time ago. But it's still hanging there. Even though Beetlejuice has already started burning helium and shrunk to a smaller size than expected, Hala isn't bothered in the slightest. Scientists call Hala the Forbidden Planet. Ooh. This discovery challenges what we thought about how planets survive near aging stars. It raises two theories. One suggests that Beetlejuice was once two stars, a white dwarf and a red giant. Hala orbited them both, and they merged before the red giant fully expanded. This allowed Hala to survive because the extra helium from the white dwarf prevented the red giant from growing too much. The second theory says that Hala formed from the debris created when the two stars merged. In this scenario, Hala would be a very young planet orbiting an elderly star. Astronomers plan to continue studying Hala and look for more planets like that. Another oddball, besides me, is called LTT 9779b. This one scares us too because it's too shiny. The planet reflects 80% of the light from its star. Regular mirrors reflect from 85 to almost 100% of light, which means that this mysterious planet should look like a rough mirror, with aluminum or silver-like reflections. This is another Neptune-sized planet. It's located 268 light-years from us and was discovered by NASA's TESS spacecraft. It completes a full rotation around its star in just 19 hours. It's so close to its star that it's scorching hot, reaching temperatures over 3,600 degrees Fahrenheit. Normally, planets this close lose their atmosphere and turn into bare rocks. But this one breaks the rules again. Now this time, we know the secret of its survival. It's because of the planet's shiny metallic clouds, which are made of glass and titanium salt. These clouds rain titanium onto its hot surface. They also reflect a lot of the light, preventing the planet from getting too hot and losing its atmosphere. It's like having a mirror shield. This planet's size also surprised scientists. It's way bigger than Earth. Other planets this close to their stars are either much bigger gas giants or small rocky planets. This planet is a smaller gas giant, and scientists didn't expect it to exist so close to its star. This is the shiniest planet ever found, even shinier than Venus. But despite its cool appearance, it's probably not a friendly place for life because of its extreme temperatures and strange metallic rain. And our final rule breaker is a planet called WASP 107b. Scientists discovered it using the James Webb Space Telescope. It's located around 208 light-years from us in the Virgo constellation. It's also fast and completes an orbit around its star in just 6 days. This is a super Neptune exoplanet. It's similar to Jupiter in some ways, including the same size and scorching hot temperatures. But the main difference is that it's much lighter, weaker, and less dense. This is the least dense planet we've discovered so far. After researching some more, we also found that it has a tail. The helium on the planet extends beyond the transit egress. The planet is slowly losing its atmosphere due to extreme ultraviolet radiation from the star. This creates a comet-like tail. So, it looks like a fluffy comet. But that was just the beginning. The planet's low density, or fluffiness, allowed astronomers to study its atmosphere in detail. They found some surprising things, like water vapor and clouds made of fine silicate particles, which are like really fine-grained sand. The planet's host star doesn't emit a lot of high-energy light. But since WASP 107b is so loose, the light can penetrate deep into its atmosphere. This creates sulfur dioxide that smell when you light a match. In other words, it's a fluffy planet that rains sand and smells like matches. The researchers think the sand clouds in the atmosphere form in a similar way to clouds on Earth. They just have droplets of sand instead of water. These sand droplets condense, fall, turn into silicate vapor in hot layers within the planet, and then rise again to form clouds once more. And, once again, this planet couldn't have formed in its current spot. Astronomers say that it likely moved closer to its star from a birth orbit because it was attracted by some heavier neighbor. It also follows a retrograde orbit, meaning it orbits in the opposite direction to its star's rotation. All these discoveries are changing how we understand planets and their atmospheres, giving us new insights into the mysteries of our own solar system. The Moon is the Earth's closest space neighbor and its only natural satellite. It likely formed when a huge Mars-sized object crashed into our planet billions of years ago. I wasn't around then. This catastrophe turned Earth into a scorching ball of molten rock. It also pushed some material into its orbit, creating the Moon. Now, this heavily cratered sphere moves around our planet. This causes high and low tides around the globe. A bit more than 1/4 the size of Earth, it's the 5th largest natural satellite in the solar system. The Moon has several phases. For example, new, full, or crescent moon, first and last quarter. But whatever the satellite looks like, you can always find it in the night sky, and sometimes even during the day. But imagine waking up at night and noticing that the Moon looks somewhat different than usual. It seems brighter and bigger. It's hardly noticeable, especially when you're half asleep. You go back to bed, unaware that instead of the Moon, you've just seen Mercury. Close up, this planet, the nearest to the Sun, is similar to our natural satellite. Its surface is littered with craters left by space rocks. Mercury is about 2/5 the size of our planet, but it's still a bit larger than the Moon. That's why the planet would have a greater influence on Earth. Nights would become brighter, high tides would become higher, and low tides, what do you think, lower? Yup. The lunar cycle, that's the time the Moon, or rather Mercury now, needs to go through all the phases, would become 14 hours shorter. But all in all, such a replacement wouldn't have any drastic consequences for our planet. But then, how about Venus? What if, instead of the familiar satellite, we swap in the third brightest natural object after the Sun and the Moon? It's often called Earth's sister planet because their mass and size are nearly the same. Venus would be as large in our sky as Earth once appeared to the Apollo astronauts when they looked at it from the Moon's surface. The morning star would be much brighter than the Moon. For one thing, the planet reflects 6 times more sunlight. Plus, it would occupy an area at least 16 times larger. That's why nights on Earth would be as bright as early twilight now. If you looked at Venus, you'd spot vague swirling patterns in the planet's yellowish-white cloud cover. Venus wouldn't become Earth's satellite. The two planets would likely orbit around their common center of mass, and this orbit would be quite eccentric, like me. But if Venus moved with the same speed as the Moon has now, the two planets would crash into each other in the nearest future. Uh-oh. Okay, let's pull another switcheroo. If Mars was up there in the sky instead of the Moon, you'd surely notice it. Even without a telescope, you'd be able to marvel at its unusual color and dark spots on its surface. And even if you didn't see the red planet, you'd still feel something unusual. Mars is half of Earth's size, but several times larger than the Moon. Replacing a smaller space body with a much bigger one would upset the delicate balance on our planet. If you were unlucky to be at the seaside when Mars took the Moon's place, you'd have to evacuate as soon as possible. Massive waves would rise in the oceans under Martian influence. They would crash against the shoreline like the largest tsunamis. Mars would be reflecting more sunlight than the Moon. Nights would be lighter. Terrestrial landscapes would have an eerie red tint. And you'd be able to admire the tallest mountain in the solar system, Olympus Mons, through a telescope. Mars isn't large enough to change the Earth's orbit dramatically, but with time, the two planets would probably begin to orbit each other, creating a binary planet system. And since Mars would literally be next door, voyages to this planet would become a reality. Okay, now think really big. If Jupiter replaced the Moon, Earth, as an independent planet, wouldn't exist anymore. It would instantly turn into another moon of the largest planet in the solar system. The only positive moment in this transformation? People would have an awesome sky view. Jupiter is dozens of times larger than the Moon. A gigantic, beautifully striped sphere would cover nearly all the horizon. If you had time to enjoy the show, you'd see yellow, brown, red, and white clouds floating in Jupiter's atmosphere. Sadly, the gas giant's gravitational pull would instantly cause severe earthquakes, volcanic eruptions, and tsunamis. Earth's mantle and crust would be drawn toward Jupiter, which would break the planet apart. It'd be stretched and compressed with such force that its surface would bulge back and forth by more than 300 feet. Unfortunately, Earth's speed is only 10% of the speed needed for us to stay in Jupiter's orbit. That's why our sluggish planet would crash into the gas giant in less than a day. Well, that sounds unpleasant, so let's not do that. Now, if Saturn were to replace the Moon, it would be a sight to behold. The planet is more than 35 times larger than our satellite. It means the giant golden globe would cover 18 degrees of the sky, and its rings would stretch even further, from horizon to horizon. Hey, if you like it, then you should have put a ring on it. Earth would be a bit further away from the gas giant than its own moon, Dione. And since Saturn is way more powerful than our planet, Earth would turn into its satellite, not the other way around. Unfortunately, Earth's rotational speed wouldn't be enough to keep up, and we'd most likely crash into the much larger planet within a day or two. But before burning up in Saturn's atmosphere, we'd have to pass through its magnificent rings. They're made up of pieces of comets, asteroids, and shattered moons. It wouldn't be an easy feat to get through this space debris. Plus, our planet would have to avoid Saturn's moons, all 53 of them. But what if the fall didn't happen, and Earth did turn into Saturn's 54th moon? Then the gas giant's gravitational pull would lead to massive tectonic shifts all over our globe. They would be tearing the planet's crust apart until there's nothing left. Not good either. Both Uranus and Neptune are ice giants. These planets are the same size, larger than Earth, but smaller than Saturn and Jupiter. They both have icy interiors, deep atmospheres, and similar color. Very beautiful bluish green. If either of these planets replaced the Moon, the consequences would be the same. So, let's flip a coin. Okay, it would be Neptune you'd see in the sky one day. Neptune is 14 times larger than the Moon. The planet would look like a bright blue hot air balloon in the sky, not only at night but during the day too. It would appear to be 15 times larger than the Sun. If everything else remained the same, a solar eclipse would seem to continue for ages. Once the Sun vanished behind Neptune's edge, our planet would be plunged into complete darkness for no less than an hour and a half. Neptune is 17 times the mass of Earth, and its gravitational pull is much stronger. That's why our planet would end up as a satellite. Yep, again. It would orbit Neptune slightly further than its own largest moon, Triton. By the way, there would be a great risk of Earth colliding with this space body. But let's assume we were lucky enough not to cross paths with Neptune satellites. Even so, there would be more than enough problems on our hands. Tides on our planet would become 1,000 times more powerful than those caused by the Moon. Neptune's gravitational force wouldn't pull Earth apart, but it would heat our planet up. The seismic activity would increase, setting off earthquakes and volcanic eruptions. And probably louse up the internet too. Okay, it seems scientists have come across a strange object in space, and they're not sure if it's a star or a planet. What we do know is that it's located 1,400 light-years away from us, and it makes us question what we thought we knew about the universe. Let me explain the dilemma here. We can tell if something is a star or a planet by considering the object's mass or the amount of stuff it has. Stars have a lot of mass, which gives them strong gravity that squeezes them tightly. Squeezing creates high temperatures inside them, causing them to shine brightly. Planets have less mass, so their gravity is weaker. They don't experience the same squeezing or high temperatures as stars. Instead, planets shine because they reflect the light from their stars, like our beautiful Earth does with our Sun, too. And this weirdo falls somewhere in between, since we consider it a brown dwarf. It's a special type of big, gaseous protostars. Brown dwarfs are usually like Jupiter in terms of their atmosphere, but they are much larger in size, about 13 to 80 times. If a brown dwarf has more than 80 times the mass of Jupiter, it can start burning regular hydrogen, just like a star. That's what usually makes stars shine brightly. But normally, brown dwarfs are not as hot as stars. Their inability to burn hydrogen has even earned them the nickname of failed stars. They burn at around 4,000 degrees Fahrenheit, which is cooler than most stars. But this object defies the norm. Its temperature measures an incredible 13,900 degrees Fahrenheit. Now let's put that into perspective. The hottest day in history was reported to happen in Death Valley, California, more than 100 years ago, with a temperature of 134 degrees Fahrenheit. People back then must have felt like they were melting along with everything around them. Now imagine getting closer to the Sun, like taking a trip to Venus. Venus can reach insane temperatures of 860 degrees. It's not only about the distance, though. Mercury is the planet closest to the Sun, but it's still colder than Venus. Venus is extremely hot due to the greenhouse effect. Did you know that Venus could have been a delightful place to live a long time ago? Or at least be home to any form of life. But at some point, it started to trap carbon dioxide and eventually created this thick, smoggy oven that doesn't release heat. And that's why it's so hard to explore. The longest a probe managed to last on Venus was 2 hours. But hey, that's longer than I can do at work, and then I melt. So yeah, then you get to the Sun. Its surface burns at an incredible 9,930 degrees Fahrenheit. And what's fascinating is that this weird brown star we're talking about is hotter than that. I mean, it's not hotter than the Sun's core, whose temperatures go up to 27 million degrees, but it's still very impressive and unusual for a brown dwarf to be this hot. At least, that's what everyone thought until they realized why it was happening. The brown dwarf is remarkably close to another star that falls into the category of white dwarfs. They're so close to each other that our mysterious star makes one orbit around its white dwarf friend in just 2.3 hours. Woo! How old we'd be over there! Since they're this close, they're tidally locked like our Moon and Earth. That means one side of this brown dwarf always faces the white dwarf, and the other side is forever in darkness. Because of all this, our brown dwarf is superheated on one side only. So its day side is what got us confused. While the temperature on the night side is what you would expect from a brown dwarf. But these extreme conditions won't last long. Such a hot temperature makes the molecules in the dwarf's atmosphere break apart into individual atoms. And while its molecules are falling apart, this brown dwarf is slowly disappearing. And if you think this brown dwarf is hot, what would you say about Eta Carinae? It's a star located about 7,500 light-years away from Earth, and it belongs to an elite group of stars we call luminous blue variables. One astronomer first noticed it in the 17th century, but back then, it was just a regular medium-bright star. Almost 200 years later, another astronomer was observing it. But this time, it was a very bright star, one of the brightest ones in the sky. A few years later, it reached the highest level of brightness in a big event called the Great Eruption. When it happened, the star could be easily seen in the night sky. It released so much light, as much as is emitted in a supernova explosion. It remained like that for a couple of years, which is not what usually happens with exploding stars. After the party reached its peak, the star decided it was time to leave. It's still hesitating though, so it's still alive but dimmer than before. There's a nebula around Eta Carinae too. It is a shell made of gas and dust that formed during the Great Eruption. It even blocks some of the star's light. Eta Carinae is a binary star system. That means there are two stars that orbit around each other. One component has a temperature of about 26,500 degrees, and the other 62,500 degrees. The main star in the Eta Carinae system, which is the more massive of the two, is 100 times heavier than our Sun. Because of its enormous mass, scientists predict that this star may eventually explode in a powerful event known as a supernova. But not for another several thousand years. So, by now, you might have already guessed what the hottest thing in the universe is. Ta-da! A supernova. The supernova is what tells us that the life of a star has ended. We're talking about the most powerful explosions in space. They happen when a star that's between 8 and 40 times more massive than our Sun flops. Its core can no longer create enough energy through a process called fusion, so the star can't even handle its own gravity. It's like a stellar burnout, too much work a star can't handle, and its core just collapses. During a supernova, the temperatures in the star's core can get 6,000 times higher than in the core of the Sun. Or sometimes, a specific type of star called a white dwarf suddenly restarts its nuclear fusion, and bam, you get a supernova again. Kepler's supernova happened at the beginning of the 17th century, and it was the last really big supernova event we directly observed from Earth. On average, supernovas in our galaxy happen 3 times every century. I mean, we got a smaller supernova in 1987 too, when a blue supergiant exploded in one of the Milky Way's satellite galaxies, which we know as the Large Magellanic Cloud. This explosion was so strong, people could even observe it with the unaided eye, even though it was incredibly far, 168,000 light-years away from our home planet. What a topic for summer days, huh? But check this out. We can also talk about the hottest thing people have ever created, made in a surprising place, Switzerland. Nah, we're not talking about a super hot chocolate. A group of scientists there created a subatomic soup called a quark gluon plasma. In this experiment, the temperature got 250,000 times as hot as the Sun's core. The purpose of this experiment was to recreate the conditions that existed shortly after the Big Bang, when the universe was still in a state of chaos. Okay, let's get even more extreme. In theory, things can get even hotter. Have you heard of the Planck temperature? It's an insanely hot temperature with numbers so high we can't even imagine. A supernova is like tepid tea compared to this madness. And who even knows what the matter does at these temperatures? Okay, I'm done. Now we take you back to your regular universe. Bye now.
Have you ever wondered what it would be like if every planet in our solar system was the size of Earth? Well, it's time to dive into this mind-boggling scenario. Let's imagine what each planet would look like if they were as big as our beloved blue planet. Would the barren red landscape of Mars suddenly become a lush green oasis? Would the massive swirling gas giant Jupiter just disappear? And how would it affect our solar system as a whole? Are we all doomed? Buckle up and let's find out. The first planet on our list is Mercury, the smallest planet in our solar system. But now, forget about the moon-like Mercury. Instead, picture yourself on the surface of a super dynamic incandescent inferno. There are a lot of craters and active volcanoes around you, and right in front of you is a huge, blinding bright sun. What a nightmare! But let's break these changes down. Well, along with the size of Mercury, both its mass and gravity would increase. In that case, it's possible that Mercury would have more atmosphere. Temperatures on Mercury are extreme, not only because it's very close to the Sun, but also because of its very thin atmosphere. So during the day, the temperatures there reach 800 degrees Fahrenheit, and at night, it becomes terrifyingly cold, down to negative 290 degrees Fahrenheit. But now, when the gravity is stronger, Mercury could have a denser atmosphere, so the heat would be better distributed across the planet. And the atmosphere isn't the only thing that could make it hotter. If Mercury became bigger, it would likely experience increased internal heating due to gravitational compression. And hypothetically, its tectonic activity could increase. In other words, more interesting landscape, more mountains, and more scary active volcanoes. Congratulations, you've turned Mercury into Venus 2.0. For us, all these changes wouldn't be very pleasant. Now it would become much harder to send our spacecraft there, so it's better for Mercury to stay as it is, small, calm, and boring. Basically, the complete opposite of our next planet, Venus. So what would happen to Venus if it was Earth-sized? Actually, nothing. It wouldn't change at all because Venus is already almost the size of Earth. It's even called the Earth's twin, although twin is a big word, of course. In reality, we couldn't be more different. Venus is often called the morning star because it's so bright and visible in the sky. But don't let its beauty fool you. This planet is one of the most inhospitable places in our solar system. Its surface is hotter than a freshly baked pizza, around 900 degrees Fahrenheit, and it's covered in thick clouds of sulfuric acid that would dissolve any human who tried to visit. So, unfortunately, you won't be planning any trips there anytime soon. So let's move on to a planet that, unlike Venus, could potentially become a new home for us: Mars. Picture yourself standing on Mars's surface, watching the blue sunset and breathing in a refreshing breeze of air. Yes, you read that right, air. Moreover, you could be surrounded by plants, animals, and basically feel like you're on Earth. But how is that possible? Bigger Mars would have a stronger magnetic field and gravity. This would lead to a richer and denser atmosphere. It would likely have a wider range of gases, including oxygen. Wouldn't that be cool? Also, a denser atmosphere could distribute heat across the planet, so Mars would become much warmer and cozier. And here comes the most important change: liquid water. Mars actually has some frozen water at its poles and in subsurface reservoirs. But with a stronger gravitational pull, it could potentially stabilize liquid water on its surface. Hooray! However, it's not all fun and games. New Mars would also have a volcanic personality. It's already geologically active, but now its internal heat and pressure would skyrocket. That means more frequent and more crazy volcanic eruptions. Imagine how exciting it would be to witness such eruptions on another planet, if you manage to escape the consequences. In general, the planet could become greener and lusher, but not safer, although it would still be great to see it. But it's time to move on to the giants of our solar system. And if we're enlarging the planets before, now it's time to squeeze them really, really hard. If Jupiter became 11 times smaller, oh boy, what a disaster that would be. The first thing we'd notice is a change in gravity. And I say we'd notice because now we'd have no choice but to move somewhere. Jupiter experiences from 30 to 100 collisions with large asteroids per year. No big deal. All because of its strongest gravity, which attracts them all and protects us. But now our big protective brother has turned into a small baby. Say hi to a bunch of asteroids. Oh, and say bye-bye to Jupiter. This planet is known for its thick, swirling atmosphere. But with a weaker gravitational pull, Jupiter would probably have a hard time holding on to it. So over time, it would slowly escape into space, leaving behind a thin atmosphere composed mainly of nitrogen and oxygen. We'll also have to bid farewell to the iconic appearance of another giant, Saturn. The most noticeable difference would be the disappearance of its famous rings. Made up of small particles of ice and rock, the rings are a unique feature of Saturn. But with Earth's gravity, they would either fall onto the planet or scatter into space. Bummer. Saturn is also a gas giant, just like Jupiter. Its atmosphere is made up of mostly hydrogen and helium. But if it were Earth-sized, its gases would be compressed due to the increased gravity. This would make it much denser. That means Saturn's overall size and shape would change. Theoretically, if we squeeze Saturn hard, it could potentially become a brown dwarf. It's a type of failed star that lacks the mass to sustain nuclear fusion, but emits heat and light. So, Saturn could stop being a planet altogether. The weather on it would probably have changed too. All its crazy storms, such as the famous hexagonal storm at its North Pole, would have become weaker and calmer. The next giant is Uranus. Let's try to compress this poor fella. First off, the surface gravity on Uranus would be much weaker than it is now. Its atmosphere might also change. If Uranus was smaller, it could have a thinner atmosphere and different gases altogether. This planet is pretty chilly. with an average temperature of -353 degrees Fahrenheit. Ugh. But if it was the size of Earth, it might actually warm up a bit due to its reduced volume to surface area ratio. Don't get too excited though, it would still be way colder than the coldest spots on Earth. As you can see, gas giants don't easily go through all this shrinking, except perhaps one of them. Surprisingly, small Neptune would become much friendlier. For starters, it would probably be a rocky planet with a tiny atmosphere. That means no more gas giant, but instead, a planet that's easier for humans and critters alike to live and move around on. Speaking of movement, because of the smaller size, the gravity on this new Neptune would be almost the same as Earth's, making it a heck of a lot easier to walk and jump around. No more floating away into space. Now, the atmosphere of the original Neptune is so thick you could barely see your hand in front of your face. And the surface pressure is about 100 times that of Earth's atmosphere. But our new Neptune would be much different, with a much thinner and less dense atmosphere. It would still have some methane, water, and ammonia in it, but nowhere near as much as before. Finally, the temperature. The current Neptune is freezing, with an average temperature of about -370 degrees Fahrenheit. But if it was the same size as Earth, it would likely be much warmer, just like Uranus. Ah, that's more like it. What a planet that would be. That's it for the changes in the planets. But what would happen to the entire solar system if we made all the planets so small? It's hard to predict, but it's clear that their gravity and orbits could change a lot. It's unlikely that any of them would have flown into outer space, or crashed into each other, or something like that. But many of their orbits would probably become quite unstable, and the number of collisions with asteroids would have increased significantly. Of course, all this is purely speculation. It's not like we can actually test all this. But it's still a pretty interesting thought experiment, and it makes you appreciate just